Hello there, and welcome to Science for Sleep, a place where curiosity is allowed to slow down, where questions are never rushed, and where science is explored gently, without urgency or pressure to reach conclusions too quickly. This is a space for winding down, for letting the day loosen its grip, and for allowing ideas to drift through your thoughts without needing to hold on to them too tightly. Whether you're listening with the lights already dimmed, or simply taking a quiet moment before rest, I am glad you are here. Tonight, we are going to sit with a question that sounds bold at first, maybe even a little rebellious, but does not need to be answered sharply or defensively. Instead, it can be approached the same way we approach sleep itself, slowly, patiently, with curiosity rather than resistance. The question is this: is the Big Bang Theory actually wrong? Not misunderstood, not incomplete, not simplified for textbooks, but wrong in a deeper sense. Or perhaps more gently, could it be less certain than we are often led to believe? Now, before your mind jumps ahead, before it starts assembling arguments or recalling headlines or imagining dramatic claims about scientists tearing up chalkboards, let's pause for a moment. This is not a debate. It is not an attack on science. It is not an attempt to replace one confident story with another. Instead, this is an invitation to look closely at how scientific ideas are formed, how they grow, and how they sometimes change shape when new questions refuse to stay quiet. The Big Bang is often presented as a settled fact, the opening scene of the universe complete with a date, a temperature, and a clear sequence of events. Everything began, we are told, around 13.8 billion years ago, in a state that was incredibly hot, incredibly dense, and expanding rapidly. From that early state came space, time, matter, galaxies, stars, planets, and eventually us. It is a powerful story, and like all powerful stories, it can feel reassuring to believe that the beginning of everything has already been explained. But science rarely works like a finished storybook. It works more like a notebook filled with crossed-out ideas, margin comments, and questions written in pencil rather than ink. The Big Bang Theory itself emerged not because scientists wanted a dramatic origin story, but because certain observations refused to fit old ideas about the universe being static and unchanging. Over time, those observations were organised into a framework that worked remarkably well. And yet, working well is not the same thing as being complete. It is not even the same thing as being unquestionably true in every possible sense. As we move through this exploration together, we will not rush to conclusions. We will not treat doubt as something dangerous or disrespectful. In science, doubt is often the starting point, not the enemy. Many of the greatest advances came from someone quietly asking, does this explanation really cover everything we see? That kind of question does not dismantle knowledge, it strengthens it. Before we go any further, let me ask you something simple. Where are you listening from right now? Are you somewhere familiar, like your bedroom or living room, or somewhere unusual, maybe travelling, maybe somewhere quiet and new? And what time is it for you at this moment? Early evening, late night, or that blurry hour where the day and night seem unsure which one is in charge? There is something fitting about thinking of the universe's beginning while each of us listens at a different point in our own small timeline. If you find this space calming, if the slow pace and gentle questioning help you unwind, you're welcome to show your support in the usual ways, with a like or a subscription. It helps this quiet corner of science reach others who might be looking for the same kind of peaceful curiosity. There is no rush though. You can always decide later, or not at all. Now, let's ease into the question itself without tension, without drama. When people hear the phrase Big Bang, many imagine an explosion, something like a cosmic firework bursting outward into empty space. That image is vivid, but it is also misleading, and even scientists spend a surprising amount of time correcting it. The Big Bang, according to the theory, was not an explosion that happened at a particular point in space. It was an expansion of space itself everywhere at once. There was no centre, There was no surrounding emptiness for it to expand into. Space was not stretching into something else. Space was stretching, full stop. Even at this early stage, the language begins to strain. Words like before, after, beginning, and expansion all come from everyday experience, and yet they are being asked to describe something that has no direct everyday counterpart. That alone should make us cautious. When a theory relies on metaphors that can never be fully accurate, there is always room for misunderstanding, and sometimes for deeper problems hiding behind familiar phrases. One of the reasons the Big Bang Theory gained so much acceptance is that it does an impressive job of explaining several major observations at once. The expansion of galaxies away from one another, the faint glow of cosmic microwave background radiation, and the relative abundance of light elements like hydrogen and helium all fit neatly within its framework. These are not small details. They are significant, measurable features of the universe. Ignoring them would be irresponsible. And yet, even with these successes, there are questions that remain awkwardly unanswered. What exactly was expanding? What does it mean for time itself to have a beginning? Why did the early universe start in such a specific state? One that allowed galaxies and stars to form rather than collapsing back into nothing or flying apart too quickly. And perhaps most unsettling of all, what, if anything, came before? In many presentations of the Big Bang, these questions are set aside with phrases like, "we don't know yet," or "physics breaks down at that point." Those phrases are honest, but they also mark the edges of the theory's reach. When a theory repeatedly runs into a wall labelled unknown, it is worth asking whether that wall is temporary, or whether it suggests that the framework itself might need adjustment. There is another layer to this discussion that often goes unnoticed. Scientific theories are not just collections of equations and data. They are also shaped by assumptions, by the tools available at the time, and by the questions scientists think are worth asking. The Big Bang Theory emerged in a period when physics was grappling with the consequences of general relativity and early cosmology. It was built using the best mathematics and observations available, but it was also built within certain conceptual limits. For example, the idea that the universe had a single, definite beginning fits comfortably with how human minds tend to think about stories. Everything starts somewhere. Every journey has a first step, but nature does not always cooperate with our narrative instincts. In other areas of physics, beginnings turn out to be far more complicated, sometimes dissolving entirely when examined closely. It is not unreasonable to wonder whether the universe's origin might belong to that category as well. You do not need to decide whether the Big Bang is right or wrong. There is no test at the end, no verdict required. Instead, you can simply notice how the question unfolds, how certainty and uncertainty coexist in science, and how even widely accepted ideas are often held together with more humility than popular explanations suggest. For now, let your attention settle. There is no need to hold on to every detail. If your thoughts wander, that is fine. You can always drift back when something catches your interest. The universe, after all, is not going anywhere, and neither is this question. For a long time now, the way we talk about the beginning of everything has followed a familiar pattern. It usually starts with confidence. Somewhere in the distant past, the universe began. Not gradually, not quietly, but decisively. A single moment when space, time, matter and energy all came into existence together. From that moment onward, everything unfolded according to understandable rules, eventually leading to stars, planets, life and curious minds asking how it all began. It is a story that feels neat, even comforting, because it gives the universe a clear opening line. That story did not emerge all at once. It was assembled slowly, shaped by observations, calculations, disagreements, and revisions. But once it took hold, it became more than just a scientific model. It became a cultural narrative. Textbooks, documentaries, museum exhibits, and casual conversations all began to repeat it in roughly the same way. The universe had a birthday. We knew when it happened. We knew roughly what it looked like, and we knew what followed next. There is nothing inherently wrong with telling science as a story. Humans understand the world through narratives. We connect causes to effects, beginnings to outcomes. When a scientific explanation fits neatly into that structure, it becomes easier to remember, easier to teach, and easier to share. Over time, though, the convenience of a story can blur the line between what a theory actually says and what we assume it must mean. When most people hear about the beginning of the universe, they imagine a moment that behaves like other beginnings they know. A spark that ignites a fire, a seed that grows into a tree, a starting gun that signals a race. Even when we are told that the Big Bang was not an explosion in space, the language surrounding it often pulls us back toward that image anyway. Words like birth, origin, and creation carry emotional weight, whether we intend them to or not. This is where the story begins to shape our expectations. If the universe began, then there must have been something like a before. If everything expanded from a hot, dense state, then it feels natural to ask what caused it. And if there was a cause, then perhaps there was something outside the universe that triggered it. These questions are not silly. They arise naturally from the way the story is framed. But they are also questions that the Big Bang Theory itself is not equipped to answer. In scientific terms, the Big Bang Theory describes the early evolution of the universe, not its ultimate origin in the philosophical sense. It tells us how the universe behaved when it was extremely hot and dense, how it expanded and cooled, and how simple particles eventually formed more complex structures. It does not explain why the universe exists at all, or why the laws of physics have the form they do. Those deeper questions often slip quietly into the gaps left by the story, where they take on a life of their own. As the narrative spread beyond the scientific community, those gaps were sometimes filled with assumptions rather than caution. Popular explanations smoothed over uncertainties to keep the story flowing. Diagrams showed a neat timeline starting at 0 and stretching forward to the present. Animations depicted a tiny glowing point rapidly expanding into galaxies. Over time, these representations became familiar enough that they started to feel literal, even though scientists themselves often emphasize their limitations. There's also the issue of authority. When a story is told repeatedly by experts, institutions, and trusted sources, it gains weight. It begins to feel settled. Questioning it can seem unnecessary or even contrarian, but in science, widespread acceptance does not mean a theory is immune to scrutiny. It means that, so far, it has explained observations better than its competitors. That distinction matters, especially when dealing with something as extreme and inaccessible as the earliest moments of the universe. The story of the beginning also reflects the tools we've used to observe the cosmos. Much of what supports the Big Bang Theory comes from looking outward and backward, using light that has travelled for billions of years. Telescopes allow us to see distant galaxies as they were long ago. Measurements of background radiation give us clues about conditions in the early universe. These are powerful tools, but they are indirect. We are reconstructing a past we cannot observe directly, using signals that have been altered by time, distance, and cosmic processes. Because of that, the story is always an interpretation, not a recording. It is a best fit explanation based on available evidence, filtered through mathematical models and assumptions about how physical laws behave under extreme conditions. When the story is told too confidently, it can obscure that provisional nature. It can make it sound as though we are recounting a witnessed event rather than inferring a distant past from faint traces. Another reason the story holds such appeal is that it aligns with a broader human desire for origins. Many cultures have creation stories. Some involve gods, others involve cycles, chaos, or emergence from nothingness. The scientific story of the universe's beginning is often seen as a replacement for those older narratives. It offers a version that is grounded in observation rather than tradition. But even as it replaces them, it inherits some of their structure. There is a clear beginning. There is a sequence of events. There is a sense of progression from simplicity to complexity. These elements resonate with how humans have always tried to make sense of existence. That resonance can make the story feel intuitively right, even when parts of it are deeply counterintuitive from a physical standpoint. Within the scientific community, the story is usually told with more caveats. Researchers are careful to specify what the theory does and does not claim. They talk about epochs, parameters, and models rather than beginnings in the everyday sense. But those nuances often fade as the explanation moves outward into classrooms and media. The story becomes cleaner, more decisive, and less ambiguous. This is not necessarily a failure. Simplification is unavoidable when communicating complex ideas. The problem arises when simplification hardens into certainty, and certainty discourages curiosity. When the beginning of everything is presented as a solved problem, it leaves little room to explore alternative ideas or unresolved questions. There have always been scientists who are uneasy with the story as it is commonly told. Some objected to the implication that time itself began, arguing that this pushes physics into philosophical territory it cannot navigate. Others pointed out that the mathematics describing the earliest moments leads to infinities and breakdowns, signals that the theory is being pushed beyond its valid range. These concerns did not make the Big Bang Theory disappear, but they never fully went away either. Over time, the story has been adjusted to accommodate these issues. Concepts like cosmic inflation were introduced to explain why the universe appears so uniform and flat. Dark matter and dark energy were added to account for observed motions and expansion rates. Each addition improved the fit between theory and observation, but also made the story more complex and in some ways more fragile. It is worth noticing how these additions are often described. They are rarely framed as signs of trouble. Instead, they are presented as refinements, extensions, or missing pieces. That framing keeps the core story intact, even as it grows increasingly elaborate. Whether that is a strength or a warning sign depends on how one interprets the role of theories in science. From one perspective, this is exactly how science progresses. A basic framework is established, and then details are filled in as new evidence emerges. From another perspective, the growing number of unseen components can raise questions about whether the framework itself is the best possible one. At what point does adding complexity suggest that the underlying story might need rethinking? The way the beginning of everything is told also affects how people think about the future of cosmology. If the origin is settled, then the remaining work is refinement. Better measurements, more precise data, smaller error bars. If the origin is still open, then deeper conceptual changes may lie ahead. Those two outlooks lead to very different scientific cultures. None of this means that the Big Bang Theory is obviously wrong or on the verge of collapse. It means that the story we tell about it may be more confident than the evidence strictly allows. It means that the narrative has taken on a life of its own, shaped by repetition, pedagogy, and cultural expectations. As you listen to this, you might notice your own reactions to the idea of questioning the beginning story. Perhaps there is curiosity. Perhaps there is discomfort. Perhaps there is a sense that some ideas feel too foundational to question. All of those reactions are understandable. The beginning of everything is not a small topic. It touches on identity, meaning, and our place in the universe. The story we have been telling ourselves did not emerge overnight, and it will not change overnight either. What matters is recognizing that it is a story shaped by evidence, interpretation, and human perspective, not a final word carved into the structure of reality. When people say the Big Bang, they often feel as though they are naming a single event, something sharp and dramatic that happened once and then was over. The phrase itself encourages that impression. It sounds sudden, it sounds violent, it sounds like the universe arrived with a noise. But when scientists use the term carefully, they are not describing a bang in the ordinary sense at all. They are referring to a model, a framework, a way of describing how the universe behaved when it was very different from how it is now. At its core, the Big Bang Theory is not a theory about how the universe came into existence from nothing. It is a theory about how the universe has evolved from an early, hot, dense state into its current, cooler, more spread out form. That distinction is easy to miss because everyday language tends to blur it. Saying, the beginning of the universe feels natural, but it quietly adds claims that the theory itself does not strictly make. What scientists mean by the Big Bang is that when we trace the expansion of the universe backward using the equations of general relativity and modern cosmology, we find that the universe becomes denser, hotter, and more compact the farther back we go. Galaxies move closer together. Radiation becomes more energetic. Matter exists in simpler forms. Eventually, the mathematics points toward an extreme state where densities and temperatures become enormous. That is the region we label the Big Bang. What they do not mean is that there was a point in space where everything exploded outward into emptiness. There was no center of the expansion. Every region of space was closer together than it is now. From the perspective of any galaxy, all other galaxies appear to be moving away, not because they were flung outward from a central blast, but because the space between them has been stretching. This is one of the most persistent misunderstandings. Even people who are familiar with the theory sometimes imagine the universe expanding into something, like a balloon inflating into surrounding air. In the cosmological picture, there is no surrounding space that the universe is growing into. Space itself is what is expanding. Asking what the universe is expanding into is a bit like asking what the surface of a balloon is expanding into if you only live on the surface. From within the system, the question does not quite apply. Another important clarification concerns time. When people hear that the Big Bang happened 13.8 billion years ago, they often imagine a timeline stretching backward into a moment before that. They ask what existed before the Big Bang, what caused it, or what was happening just prior. These questions feel unavoidable, because our experience of time always includes a before. However, according to the standard cosmological model, time itself is part of what is described by the expansion. When we extrapolate backward to the earliest moments the equations can handle, time as we understand it reaches a boundary. That does not necessarily mean time truly began at that moment. It means that our current theories cannot meaningfully describe anything earlier. This is an important difference. Saying we cannot describe what came before is not the same as saying there was nothing before. The first is a statement about the limits of our models. The second is a statement about reality itself. The Big Bang theory makes the first claim, not the second, even though popular explanations often slide toward the second without much warning. The phrase Big Bang also tends to suggest a singular, sharply defined instant. In practice, the theory describes a sequence of conditions over a very short but non-zero span of time. Physicists talk about fractions of a second after the Big Bang, during which different processes occurred. Forces separated, particles formed, energy cooled. Even in the earliest moments we can describe, there is structure and change, not a frozen point. The idea of a singularity, an infinitely dense point where the equations blow up, is often treated as the beginning itself. In reality, most physicists regard singularities as signs that a theory has reached its limit. In other areas of physics, when equations produce infinities, it usually means the model is incomplete. Something important has been left out, often a deeper theory that smooths out the extremes. The singularity associated with the Big Bang is widely viewed in this way, not as a literal description of reality. What the Big Bang does mean, very concretely, is that the universe was once much hotter and denser than it is now. This claim is supported by several independent lines of evidence. One of the strongest is the cosmic microwave background, a faint glow of radiation that fills the universe. This radiation is remarkably uniform, with tiny variations that carry information about early cosmic conditions. Its existence and properties match predictions made by Big Bang cosmology long before it was observed in detail. Another piece of evidence comes from the relative abundances of light elements. hydrogen, helium, and traces of lithium appear in proportions that align with calculations of nuclear reactions occurring in a hot early universe. These calculations depend on well-tested physics, and their agreement with observation is one of the theory's major successes. When scientists point to these achievements, they are not exaggerating. The Big Bang model explains a great deal with a relatively compact set of assumptions. Still, even here, it is important to be precise about what is being explained. The theory accounts for the universe's expansion history, its large-scale structure, and certain relics of its early state. It does not explain why the laws of physics take their particular form. It does not explain why the initial conditions were suitable for galaxies and life to emerge. It does not explain whether the universe is unique or one of many. Those questions lie outside its scope. Another thing people often assume is that the Big Bang theory represents a single, unchanging idea. In fact, it has evolved significantly over time. Early versions were simpler and left many puzzles unresolved. Later developments added mechanisms like cosmic inflation, which proposes a brief period of extremely rapid expansion very early on. Inflation helps explain why the universe appears so uniform and why its geometry seems close to flat. It also introduces new assumptions and new unanswered questions. When inflation is discussed, the phrase "the Big Bang" becomes even more ambiguous. Does it refer to the moment inflation began, the moment it ended, or the subsequent hot, dense phase? Different researchers use the term differently, sometimes without clarifying which phase they mean. This can create confusion even within scientific discussions, let alone in public explanations. There is also a tendency to treat the Big Bang as synonymous with the origin of everything, including the laws of physics themselves. Some speculative ideas suggest that physical laws may have emerged or changed during the early universe. Others assume the laws were already in place. The standard Big Bang model does not settle this issue. It typically assumes known laws and applies them backward as far as they seem reliable. Beyond that, it remains silent. Because of this, criticisms of the Big Bang often talk past what the theory actually claims. When someone says, "The Big Bang doesn't explain what caused the universe," they are pointing out a real gap, but not necessarily a flaw within the theory's intended domain. When someone says, "The Big Bang violates common sense," they may be reacting to misleading imagery rather than to the mathematics itself. On the other hand, defenders of the theory sometimes overstate its reach. They may speak as though the origin problem has been solved, when in reality it has been reframed. The language used can give the impression that science has answered questions it has actually set aside for future work. All of this makes the phrase, "the Big Bang," do a lot of heavy lifting. It compresses a complex set of ideas, equations, observations, and assumptions into two words that invite misunderstanding. It is useful shorthand, but it is also a source of confusion. As you sit with this, it may help to think of the Big Bang not as a moment, but as a description of a trend. The universe has been expanding and cooling. It was once denser and hotter. Beyond a certain point, our current descriptions lose their reliability. That is the heart of the model. Everything else, the imagery, the timeliners, the dramatic language, are ways of trying to make that abstract picture accessible. This distinction becomes especially important when people ask whether the Big Bang is wrong. If by wrong we mean that the universe is not expanding from a hotter, denser past, then the evidence strongly suggests that it is not wrong in that sense. If by wrong we mean that it provides a complete account of the universe's ultimate origin, then it was never meant to do that in the first place. Recognizing what we mean and what we do not mean when we say the Big Bang allows the discussion to become calmer and more precise. It shifts the focus away from dramatic claims and toward the actual content of the theory. It also opens the door to asking better questions about the limits of our models and the possibilities that might lie beyond them. Long before the phrase Big Bang became familiar, long before it settled into textbooks and documentaries, scientists were not looking for a beginning at all. They were trying to understand what kind of universe they were living in right now. The idea that the universe might have a history, that it might change on the larger scales, was not obvious. For centuries, the prevailing assumption was that the cosmos was eternal and largely unchanging. Stars might be born and die, planets might form and fade, but the overall structure of the universe was assumed to be stable, fixed, and timeless. What shifted that assumption was not a single dramatic discovery, but a collection of strange, often unsettling observations that did not fit comfortably within the older picture. None of them announced themselves as evidence of a cosmic beginning. At first, they were puzzles, technical annoyances, odd results that made astronomers pause, recheck their instruments, and wonder whether they had made mistakes. One of the earliest cracks appeared when astronomers began to study the light coming from distant galaxies in more detail. Light carries information not just about where something is, but how it is moving. When an object moves away from us, the light it emits is stretched, shifting toward the red end of the spectrum. This effect, known as redshift, was already understood in other contexts. It had been measured in stars moving within our own galaxy. What surprised astronomers was how consistently it appeared in galaxies far beyond the Milky Way. As telescopes improved and observations expanded, a pattern began to emerge. The farther away a galaxy was, the more its light appeared to be redshifted. At first, this was interpreted cautiously. Distance measurements were uncertain. The universe beyond our galaxy was still largely unexplored. But as the data accumulated, the trend became harder to dismiss. Distant galaxies were not just moving randomly. They were, almost without exception, moving away. Even more unsettling was the fact that this recession did not seem to have a preferred direction. Galaxies were not streaming away from a central point in the sky. Instead, wherever astronomers looked, galaxies appeared to be receding from each other. From Earth's perspective, everything else seemed to be moving away, as though the universe itself was swelling. This observation alone did not demand a Big Bang. It did, however, challenge the idea of a static universe. If galaxies were moving apart, something had to explain why. One possibility was that galaxies were simply flying through space, like debris from some ancient explosion. Another possibility, more subtle and far more radical, was that space itself was changing. The mathematical framework for that second idea had already been developed, though few realized how relevant it would become. General relativity, with its flexible conception of space and time, allowed for solutions in which the universe could expand or contract. When those equations were applied to cosmology, they naturally produced models of a dynamic universe. At the time, even the theory's creator reportedly found this unsettling and attempted to modify the equations to keep the universe static. The mathematics suggested expansion. The observations suggested recession. Slowly, reluctantly, the pieces began to align. Still, expansion alone does not automatically imply a beginning. An expanding universe could, in principle, have been expanding forever. The idea that expansion pointed back to a hot, dense early state required further evidence. That evidence arrived in a form so quiet and unassuming that it was almost missed entirely. In the middle of the 20th century, engineers working with radio antennas stumbled upon a persistent background noise. No matter where they pointed their equipment, no matter the time of day or the season, a faint hiss remained. At first, it was treated as a technical problem. The antenna was cleaned, components were replaced, even nesting animals were blamed. Nothing removed the signal. Eventually, it became clear that the noise was not coming from Earth, the Sun, or the Milky Way. It was coming from everywhere, uniformly. The sky itself seemed to glow faintly in radio frequencies. This glow turned out to be one of the most significant discoveries in modern cosmology. According to theoretical work done years earlier, a universe that had once been extremely hot should still carry a thermal afterglow. As the universe expanded and cooled, that radiation would stretch into longer wavelengths, eventually becoming microwave radiation. The predicted temperature was only a few degrees above absolute zero. The measured signal matched that prediction remarkably well. This radiation, now known as the cosmic microwave background, did not just exist, it had specific properties. Its spectrum matched that of a cooling thermal source. Its uniformity suggested that the early universe had been remarkably even in temperature. Tiny variations in that uniformity hinted at the seeds of later structures, the slight differences in density that would eventually grow into galaxies and clusters. It is difficult to overstate how strange this evidence was. The universe, it seemed, remembered being hot. It carried a fossil imprint of an earlier state, one that could not be explained by stars or galaxies alone. This was not light emitted by objects within the universe. It was light emitted by the universe itself long before stars had formed. Another line of evidence came from the relative amounts of certain elements found throughout the cosmos. Hydrogen and helium dominate the universe by a wide margin. Heavier elements are present, but in much smaller quantities. This distribution is not arbitrary. Nuclear physics predicts that in a hot, dense early universe, only certain elements could form in significant amounts. The predicted ratios of hydrogen to helium matched observations with surprising accuracy. Stars can produce heavier elements over time, but they cannot easily account for the observed abundance of helium across the universe. The simplest explanation was that much of this helium formed very early, under conditions that no longer exist. Again, the universe appeared to be carrying chemical evidence of a hotter, denser past. Individually, each of these observations might have been explained away with enough creativity. Together, they formed a pattern that was difficult to ignore. Expansion, background radiation, elemental abundances, all pointed toward a universe that was once radically different. What made this evidence particularly compelling was that it came from different domains of physics. Astronomy, thermodynamics, nuclear physics, and relativity all converged on the same broad picture. That kind of convergence is rare. When independent lines of inquiry point in the same direction, scientists tend to pay attention. Even so, acceptance was not immediate or universal. Alternative ideas existed. Some proposed steady-state models in which the universe expanded but maintained constant density through the continuous creation of matter. These models could explain expansion without a beginning. For a time, they competed seriously with Big Bang cosmology. The cosmic microwave background dealt a severe blow to those alternatives, explaining that radiation without an early hot phase required increasingly contrived assumptions. Over time, the balance of evidence shifted decisively. The Big Bang framework, despite its unanswered questions, explained more with fewer assumptions. It is important to notice what kind of evidence convinced scientists. It was not philosophical appeal. It was not a desire for a dramatic origin story. It was a set of measurements that stubbornly refused to fit a timeless universe. At the same time, this evidence has limits. It tells us that the universe was hot, dense, and expanding. It does not tell us how or why those conditions arose. It does not tell us whether they were the first conditions or simply one phase in a longer story. The evidence supports a specific range of conclusions, not every conclusion that people sometimes draw from it. There's also an important symmetry in how this evidence works. It supports the idea that the universe evolved from a hot, dense state. It does not directly observe that state itself. We infer it. We reconstruct it. We build models that, when run backward, match the traces we see today. This reconstruction relies on assumptions about how physical laws behave under extreme conditions. Most of the time, those assumptions work well, but there are regimes, especially at very high energies and densities, where existing theories are known to be incomplete. When scientists speak cautiously about the earliest moments, this is why. The strange evidence that led to the Big Bang theory is strong, but it is not omnipotent. It answers certain questions very well. It leaves others open. Recognizing this balance is essential for understanding both why the theory became dominant, and why questions about its ultimate completeness remain reasonable. As you sit with this, it may help to let go of the idea that scientists were convinced by a single proof. Instead, imagine a slow accumulation of clues, each one nudging the picture in the same direction. None of them demanded a beginning outright. Together they suggested a universe with a deep past, one that could be traced back to conditions far removed from anything we experience today. One of the most stubborn images associated with the Big Bang is the idea of an explosion. It is an image that sneaks in quietly, reinforced by language, illustrations, and even the name itself. A bang suggests a center, a violent outward rush, debris flying into surrounding emptiness. It feels intuitive, almost unavoidable, because explosions are something we understand from everyday life. Fireworks burst, bombs detonate, engines backfire. When we hear that everything began with a big bang, the mind fills in the rest automatically. And yet, this picture is almost completely wrong. The misunderstanding is not a small detail or a pedantic correction. It goes to the heart of what the theory actually describes. Clearing it up changes how we think about space, motion, and the very meaning of expansion. It also reveals why so many questions about the Big Bang feel confusing or unanswerable when framed in the wrong way. To begin untangling this, it helps to set aside the idea of an explosion entirely. An explosion happens at a location. It occurs within space. There is something before it, something around it, and something afterward. A firework explodes at a point in the sky. Shrapnel from an explosion moves through the surrounding air. Even the largest explosions we can imagine still take place inside a pre-existing environment. The expansion described by the Big Bang theory is fundamentally different. It is not something happening in space, it is something happening to space. This distinction sounds subtle at first, but it changes everything. When cosmologists talk about the universe expanding, they're not saying that galaxies are flying outward through a fixed cosmic arena. They're saying that the distances between galaxies are increasing because the fabric of space itself is stretching. The galaxies are, in a sense, being carried along rather than hurled outward. A common way to picture this is with an analogy, though even analogies have limits. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart. From the perspective of any one dot, all the others appear to be receding. There is no special dot at the center of the expansion on the surface itself. The expansion happens everywhere on the surface at once. Importantly, the dots are not moving across the surface under their own power. The surface they sit on is changing. In the cosmological case, galaxies are like those dots. They are mostly at rest relative to their local space, but the space between them grows. That is why distant galaxies appear to recede faster than nearby ones. It is not because they were flung outward with greater force. It is because there is more expanding space between us and them. This is why astronomers can measure a consistent relationship between distance and recession speed. The farther away a galaxy is, the more space there is between us and it, and the more that space has expanded during the light's journey to us. If the universe were the result of an explosion, we would expect a very different pattern. There would likely be a central region with debris moving fastest, slowing as it spreads out. There might be observable asymmetries, preferred directions, or gradients pointing back to a center. None of this is observed. On large scales, the universe looks remarkably uniform in every direction. This uniformity was one of the clues that pushed scientists away from explosion-based thinking in the first place. An explosion in space produces structure and direction. The observed universe does not behave that way. Another common question that arises from the explosion picture is, what did the universe explode into? It is a natural question, and one that feels unanswered in many explanations. But within the correct framework, it is not really a meaningful question. If space itself is expanding, there is no external container that it is expanding into. There is no outside edge moving into emptiness. This is deeply unintuitive because we are used to objects having boundaries and surroundings. Our experience is built entirely within space, so imagining space itself as dynamic requires letting go of familiar mental scaffolding. When people ask what lies beyond the edge of the universe, or what space is expanding into, they are often unknowingly clinging to the explosion metaphor. Within the standard cosmological model, the universe does not need an outside. It is not embedded in a larger space in the way objects are embedded in rooms. Space is the arena, not a thing within an arena. This does not mean the universe must be infinite, nor does it mean it must have edges. Both finite and infinite models are possible, depending on the geometry of space. What matters here is that expansion does not require a surrounding void. Another misunderstanding tied to the explosion idea involves the notion of a starting point. People often imagine a tiny, incredibly dense speck that then blew outward, becoming larger over time. This image suggests that the early universe was small in size, confined to a particular region. In reality, the theory does not require the universe to have been small in that sense. The universe could have been infinite even in its earliest hot, dense phase. Expansion describes how distances change, not how large the universe is overall. An infinite universe can expand just as easily as a finite one. Every distance increases, even though there is no boundary enclosing the whole. This again clashes with explosion imagery, which relies on finite objects growing outward. When that imagery is applied to cosmology, it creates confusion where none is required. There is also a misconception that expansion means everything is moving away from everything else in the same way. On smaller scales, this is not true. Galaxies bound together by gravity do not expand away from one another. Stars within galaxies do not drift apart because of cosmic expansion. Atoms do not stretch. The expansion becomes noticeable only on very large scales, where gravity is weak enough that the stretching of space dominates. An explosion, by contrast, would affect everything within its range. It would tear structures apart indiscriminately. The fact that cosmic expansion leaves local structures intact is another sign that we are dealing with a very different phenomenon. Understanding this helps resolve another common confusion. People sometimes imagine that galaxies are racing through space at incredible speeds, approaching or exceeding the speed of light. In reality, the apparent superluminal recession of very distant galaxies arises because space itself is expanding. The galaxies are not locally breaking the speed limit set by relativity. The rule applies to motion through space, not to the expansion of space. Again, this distinction disappears if one insists on thinking in terms of an explosion. Explosions involve objects moving through space, subject to familiar constraints. Expansion involves the geometry of space changing, which plays by different rules. The explosion picture also encourages the idea that the Big Bang was loud, bright, and chaotic in a way that resembles a detonation. In truth, there was no sound because sound requires a medium, and there were no ears to hear it even if there had been. The early universe was hot and energetic, but its behavior was governed by physical laws, not violent randomness. The word bang was originally coined somewhat mockingly by a scientist who favored a different cosmological model. It stuck because it was memorable, not because it was accurate. Over time, the name shaped public understanding more than many of the careful explanations that followed. Once the explosion metaphor takes hold, it becomes difficult to ask sensible questions. People ask where the explosion happened, what caused it, and what the debris is expanding into. These questions feel profound, but they're based on a category error. They treat expansion as motion through space rather than change of space. Clearing up this misunderstanding does not answer every question about the universe's early history. In fact, it often exposes new ones. If space itself is expanding, what exactly is space? Why can it stretch? What determines the rate at which it expands? These are deep questions that lead directly into modern cosmology and fundamental physics. They also connect to unresolved problems. For example, the equations describing expansion allow many possible behaviors. The observed expansion rate, its acceleration, and its early rapid phases are not uniquely determined by simple assumptions. Additional ingredients, like dark energy and inflationary fields, are introduced to account for what we see. Here too, misunderstanding expansion as an explosion can hide important subtleties. If one imagines a single violent event that set everything in motion, it feels natural to expect expansion to slow over time as gravity pulls things back together. The discovery that expansion is accelerating came as a surprise, partly because it does not fit that intuition. In the correct framework, acceleration is a property of space's dynamics, not leftover momentum from a blast. As you sit with this corrected picture, you may notice how it softens some of the emotional weight attached to the idea of a beginning. An explosion suggests abruptness and drama. Expansion suggests gradual change. Even if that change was extreme in the early universe, it feels less like a cosmic accident and more like a process governed by structure. This shift also affects how people interpret questions about whether the Big Bang could be wrong. If one rejects the explosion image, much of what seems implausible or nonsensical about the theory falls away. What remains is a more precise, less sensational claim about the universe's evolution. At the same time, rejecting the explosion does not mean accepting everything uncritically. The expansion picture still leads back to conditions where current theories struggle. As distances shrink and densities rise, our mathematical descriptions approach regimes where quantum effects cannot be ignored. The fact that expansion is not an explosion does not magically resolve the mystery of the earliest moments. In some ways, clearing up this misunderstanding makes the remaining questions sharper rather than fuzzier. If there was no blast, no center, no outward rush into emptiness, then the origin problem becomes more abstract. It is no longer about an event happening somewhere. It is about why space has the properties it does, and why those properties led to the expansion history we observe. These are quieter questions, less cinematic but arguably more profound. They require thinking about geometry, energy, and the structure of physical law itself. They are also the questions where the Big Bang theory begins to feel less like a complete story and more like a chapter within a larger unfinished one. As we move forward, it will be useful to keep this corrected picture in mind. Many of the criticisms and alternatives to the Big Bang make sense only once the explosion metaphor has been discarded. Without doing that, it is too easy to argue against a caricature rather than against the theory as it is actually used. The idea that the universe expanded without exploding is strange, but it is also one of the most firmly grounded aspects of modern cosmology. Accepting it does not require abandoning common sense, so much as recognizing where common sense, shaped by everyday experience, stops being a reliable guide. Even after the explosion metaphor has been set aside, even after expansion is understood as something happening to space rather than within it, a number of questions remain that refuse to settle quietly. These questions are not fringe objections or philosophical nitpicks. They arise naturally from within the Big Bang framework itself, once it is taken seriously and followed as far as it can go. They are the places where the theory does not quite break, but where it begins to thin out, where explanations become tentative, conditional, or simply unavailable. One of the most persistent of these questions concerns beginnings in a more fundamental sense. If the universe was once in an extremely hot, dense state, and has been expanding ever since, it is tempting to imagine that this description can be extended all the way back to a first moment. But when scientists actually try to do this using known physics, they encounter a wall. Temperatures and densities rise without bound. Quantities blow up to infinity. Time itself seems to shrink towards zero. At that point, the equations no longer behave in a physically meaningful way. This breakdown is often described using the language of a singularity. A singularity is not an object or a place. It is a signal that a mathematical model has been pushed beyond the conditions under which it can be trusted. In other areas of physics, singularities tend to disappear when a deeper theory replaces an older one. The centre of an atom once appeared singular until quantum mechanics resolved it. Electrical forces once diverged at small distances until new principles intervened. In cosmology, the singularity associated with the Big Bang is widely interpreted in this same spirit. It marks the edge of our current understanding, not necessarily the edge of reality. The uncomfortable part is that despite decades of work, there is still no widely accepted theory that cleanly replaces the Big Bang description at those earlier scales. We know something is missing, but we do not yet know what it is. This leads directly to another uneasy question. Did time itself actually begin? The standard cosmological equations suggest that time, as defined within the model, cannot be extended beyond the earliest hot, dense phase. But this does not settle the matter. It simply reflects the structure of the equations, whether time truly had a beginning or whether this is a limitation of the mathematical framework remains open. The question is uncomfortable because it challenges the very tools used to answer it. Physics relies on time to describe change. Asking what happened before time existed risks turning language against itself. Some physicists argue that the question is meaningless. Others suspect that time may emerge from deeper, timeless processes. Still others propose that time existed before the Big Bang in some altered or hidden form. None of these possibilities has been decisively confirmed. The Big Bang theory, by itself, does not adjudicate between them. It describes a phase of cosmic history. It does not explain why that phase occurred, or whether it was the first of its kind. Closely related to this is the question of cause. Human reasoning is deeply causal. We expect events to have explanations rooted in prior events. When presented with a theory that seems to describe the origin of everything, it is almost impossible not to ask what caused it. What set the expansion in motion? Why did the universe begin in a state that allowed it to evolve as it did? Within the Big Bang framework, these questions have no clear answers. The theory does not identify a triggering mechanism. It does not describe a prior state that led naturally to the hot, dense beginning. Attempts to supply such explanations usually require going beyond the standard model of cosmology, introducing speculative ideas that are still under investigation. Some researchers propose quantum processes that could give rise to universes spontaneously. Others suggest that the Big Bang was not the first event, but a transition from an earlier phase, such as a contracting universe or a previous cycle. These ideas are intriguing, but they are not yet established in the same way as the expansion history itself. Another uncomfortable issue lies in the initial conditions of the universe. Even if one accepts that the universe began in a hot, dense state, the specific properties of that state are puzzling. The early universe appears to have been remarkably uniform. Temperature differences across vast regions were extremely small. Density variations were tiny. Yet those small variations were precisely tuned to allow structure to form later. This apparent fine balance raises questions. Why was the universe so smooth early on? Why were the initial fluctuations neither too large nor too small? If they had been much larger, the universe might have collapsed quickly into black holes. If they had been much smaller, galaxies might never have formed. Cosmic inflation was proposed partly to address this issue. A brief period of rapid expansion early in the universe's history could smooth out irregularities and explain the observed uniformity. Inflation also helps explain why the geometry of the universe appears close to flat. But inflation introduces its own questions. What caused inflation to start? What caused it to end? Why did it produce the specific pattern of fluctuations we observe? Inflation works well as a mechanism, but it shifts the discomfort rather than eliminating it. The need for special initial conditions is replaced by the need for special inflationary conditions. Some versions of inflation lead naturally to multiverse scenarios in which many regions of space undergo inflation in different ways. This can explain certain observations statistically, but it also raises philosophical and scientific concerns about testability. Another question that sits uneasily within the Big Bang framework involves the laws of physics themselves. The theory assumes that known physical laws apply, at least approximately, during the early universe. But at extremely high energies, those laws are expected to merge or change. Gravity, quantum mechanics, and other forces are described by theories that are not yet fully unified. This creates a gap. The Big Bang model relies on general relativity to describe expansion, but general relativity does not incorporate quantum effects. At early times, quantum effects cannot be ignored. The lack of a complete theory of quantum gravity means that descriptions of the very early universe are provisional at best. As a result, statements about what happened at the earliest times often rest on extrapolations that may not hold. Scientists are aware of this, and they phrase their conclusions carefully in technical contexts. In popular explanations, however, this caution can be lost, giving the impression of certainty where there is still active uncertainty. There is also the matter of entropy, which connects cosmology to thermodynamics. The universe appears to have started in a low entropy state. This is surprising because high energy systems often correspond to high entropy. The fact that the early universe was both hot and highly ordered is one of the deepest puzzles in modern physics. This low entropy beginning underlies the arrow of time. It explains why time seems to flow in one direction, from past to future, with increasing disorder. But the Big Bang theory does not explain why the universe began in such a special state. It takes it as a given. Some physicists argue that this question may be unanswerable within current frameworks. Others suspect that a deeper theory will reveal a reason. For now, it remains one of the most uncomfortable aspects of the story, because it touches not just on cosmology, but on the nature of time itself. Another source of unease is observational limitation. The universe has a finite age, and light travels at a finite speed. This means there is a limit to how much of the universe we can observe. Beyond a certain distance, regions of space are causally disconnected from us. We cannot receive information from them, even in principle, given the universe's expansion. This cosmic horizon means that our picture of the universe is necessarily incomplete. We infer global properties from a limited sample, while there are good reasons to believe that the observable universe is representative of the whole. This assumption cannot be directly verified. The Big Bang theory relies on extrapolating local observations to the entire cosmos. Most of the time, this extrapolation works remarkably well. But when dealing with origins, even small uncertainties can loom large. The farther back we push our models, the more they depend on assumptions that cannot be directly tested. There is also the issue of uniqueness. Is our universe the only one? The Big Bang theory does not require multiple universes, but some of its extensions suggest them. Inflationary models, quantum cosmology, and string theory landscapes all hint at the possibility of many universes with different properties. If this is the case, then the Big Bang might not be a unique beginning, but one instance among many. This idea challenges the notion that cosmology can provide a single, definitive account of existence. It also complicates the question of explanation. Why does our universe have the properties it does? Perhaps because only such universes allow observers to ask the question. Whether one finds this satisfying or troubling often depends on philosophical temperament. Scientifically, the multiverse remains speculative, but its appearance as a possible implication highlights the way unresolved questions multiply as we probe deeper. None of these discomforts invalidate the Big Bang theory as a description of cosmic expansion. They do, however, limit what it can claim. The theory works extremely well within a certain domain. Outside that domain, it becomes suggestive rather than definitive. Recognizing this does not weaken science. It clarifies its boundaries. It reminds us that theories are tools, not final answers. They organize evidence, make predictions, and guide further inquiry. They are not required to satisfy every curiosity, especially those that reach beyond current observational and theoretical reach. You may notice that these uncomfortable questions do not point in a single direction. They do not all suggest the same alternative. Instead, they form a landscape of uncertainty surrounding the Big Bang's earliest moments. Some questions may eventually be answered by new data. Others may require new conceptual frameworks. Some may remain open indefinitely. What matters for now is that these questions exist, that they are taken seriously by scientists, and that they arise not from misunderstanding the theory, but from understanding it well enough to see where it stops. When people hear that the universe has a beginning, the mind almost automatically tries to look past it. There is a strong pull to imagine something on the other side of that boundary, some earlier state, some hidden chapter just out of view. This instinct is so natural that it shows up even in the language scientists use, despite their best efforts to be precise. Phrases like, "before the Big Bang," slip into conversations, lectures, and articles, even though they point directly at a region where the theory itself falls silent. The uncomfortable truth is that, within the standard Big Bang framework, there is a limit beyond which the theory simply cannot see. It is not that there is a veil we have not yet lifted, or a telescope we have not yet built. It is that the mathematical tools used to describe the universe lose their meaning when pushed too far back. The equations do not smoothly extend into an earlier chapter. They stop offering sensible answers altogether. This is one of the most difficult ideas to sit with, because it runs against how we normally think about knowledge. Usually when we say we cannot see something, we assume it is because of a practical limitation. We lack data, we lack resolution, we lack the right technology. In this case, the limitation is deeper. It is built into the structure of the theory itself. The Big Bang model relies heavily on general relativity to describe how space and time behave on cosmic scales. General relativity treats space and time as a flexible geometry that responds to energy and matter. It works extraordinarily well for describing planets, stars, galaxies, and the large-scale expansion of the universe, but it was never designed to handle situations where quantum effects dominate. As we trace the universe backward toward earlier and earlier times, we inevitably reach conditions of extreme density and temperature. At those scales, quantum effects are no longer small corrections, they become central. Particles behave less like points and more like probabilistic clouds. Energy fluctuates in ways that classical descriptions cannot capture. In this regime, general relativity on its own is no longer sufficient. When scientists say the theory cannot see past a certain point, this is what they mean. The mathematical framework breaks down. Space and time, as defined by the theory, stop behaving in ways that can be reliably calculated. The notion of a smooth timeline extending backward becomes questionable. This breakdown is often associated with the idea of a singularity. In the equations, quantities such as density and curvature grow without bound as one approaches the earliest moment. Time appears to shrink towards zero. But most physicists do not believe that reality actually contains infinities in this sense. Instead, infinities are taken as warning signs. They tell us that a theory is being asked to describe something it was never equipped to handle. There is a temptation to treat the singularity as a real event, the literal beginning of everything. This temptation is understandable, because the equations seem to point there, but history suggests caution. In other areas of physics, singularities have repeatedly turned out to be artifacts of incomplete theories. When a deeper framework is found, the singularity often dissolves into something finite and well-behaved. This is why many cosmologists are careful with their language. They do not say that the universe definitely began at singularity. They say that the Big Bang model cannot be extended past a certain point without new physics. That difference matters. The phrase, "before the beginning," is especially tricky. If time itself is part of what the Big Bang model describes, then asking what happened before time existed may not be a meaningful question within that framework. It is a bit like asking what is north of the North Pole. The question assumes a continuation of a concept that has reached its definitional limit. This does not mean that nothing existed, or that no earlier state is possible. It means that our current way of describing time cannot reach that far. There could be something before the Big Bang in a sense that does not align with everyday notions of before and after. Or there could be a different structure altogether, one in which time behaves differently or emerges from more basic relationships. Various ideas have been proposed to fill this blind spot. Some suggest that the universe went through a contracting phase before expanding, making the Big Bang a transition rather than a creation. In these scenarios, the universe shrinks, reaches a minimum size and then rebounds. The expansion we observe would be the aftermath of that bounce. Other proposals imagine a universe that is eternal, with no beginning or end, but with phases that resemble Big Bang-like events. In such models, what we call the Big Bang is just one episode in a much longer story. The universe may have experienced many expansions and contractions over vast timescales. There are also ideas rooted in quantum cosmology, where the universe arises from quantum processes that do not require a classical notion of time at all. In these views, the universe does not begin in the usual sense. Instead, it transitions from a quantum state that cannot be described using ordinary temporal language. These ideas are fascinating, but they remain speculative. They are attempts to peer beyond the edge of the Big Bang model using incomplete tools. None of them has yet achieved the level of empirical support that the expansion history of the universe enjoys. That does not make them wrong. It simply places them in a different category of scientific inquiry. What is important here is recognizing that the Big Bang theory itself does not choose between these possibilities. It does not tell us whether there was a before. It does not tell us whether the universe emerged from nothing, from something, or from a state that does not fit either label. It tells us what happened after the universe entered a phase we can model with confidence. This limitation often frustrates people, because the beginning feels like the most important part of the story. If we know how everything evolved, why can we not know how it started? The answer lies in the nature of scientific explanation. Science builds models that connect causes to effects within a defined domain. When that domain ends, the explanations end with it. There is also a psychological dimension to this discomfort. Humans are deeply oriented toward origins. We ask where things come from. We trace lineages. We look for first causes. When confronted with a theory that refuses to provide a clear origin, it can feel unsatisfying, even evasive. But this refusal is not a flaw in the theory. It is an honest acknowledgement of its limits. Pretending to know what lies beyond those limits would be far more misleading than admitting uncertainty. Another reason the theory cannot see past the beginning has to do with observation. The universe has been expanding for a finite amount of time. Light from the earliest observable epoch has only just reached us. Beyond that, earlier signals are either too energetic, too scrambled, or simply inaccessible given the universe's evolution. The cosmic microwave background represents the oldest light we can observe directly. It comes from a time when the universe became transparent to radiation. Before that, the universe was opaque. Photons could not travel freely. Any information from earlier times is hidden from direct observation. This observational horizon is not just a technical inconvenience. It is a fundamental feature of an expanding universe. Even with perfect instruments, there are limits to what can be seen. Models can extrapolate beyond those limits, but extrapolation is not observation. This means that questions about what happened before the Big Bang are doubly constrained. The theory lacks the tools to describe that regime, and the universe lacks a clear way to communicate information from it. Any answer must rely on indirect reasoning, mathematical consistency, and philosophical assumptions about what kinds of explanations are acceptable. Some scientists argue that this makes the question unscientific. Others disagree, pointing out that many areas of physics began as speculative attempts to explain phenomena beyond immediate observation. The boundary between scientific and philosophical inquiry is not always sharp, especially at the edges of cosmology. It is also worth noticing how the language of beginnings influences debates about whether the Big Bang could be wrong. If one assumes that the theory claims to describe the absolute origin of everything, then its inability to see past that origin looks like a failure. If one understands the theory as a description of an early phase of cosmic evolution, then its silence about earlier phases is not a problem. It is simply outside its scope. This distinction often gets lost in public discussions. Critics and defenders alike sometimes argue over claims the theory does not actually make. Clarifying what the Big Bang cannot see past helps ground the conversation in what is genuinely at stake. As you reflect on this, you may notice a shift in how the idea of a beginning feels. It becomes less like a sharp edge and more like a horizon. Beyond a horizon, there may be land, water, or something entirely unexpected. The fact that it is out of view does not mean it does not exist. It means our current position does not allow us to see it clearly. In cosmology, horizons are not just metaphors. They are real features of the universe's structure. There are limits to causality, limits to observation, limits to explanation. Accepting those limits is part of doing honest science. This acceptance does not stop inquiry. It redirects it. Instead of asking for definitive answers where none can yet be given, researchers look for clues that might hint at deeper structures. They search for signatures in the cosmic microwave background, patterns in large-scale structure, and theoretical frameworks that can unify gravity and quantum mechanics. Each of these efforts is, in a sense, an attempt to glimpse something before the beginning, without pretending to know exactly what that phrase means. They are careful steps taken at the edge of understanding, where humility matters as much as ambition. When discussions of the Big Bang reach their most difficult point, they almost always circle back to a single word that carries far more weight than it seems at first glance: singularity. It sounds technical, distant, almost abstract, and yet it marks the exact place where our current understanding of the universe stops behaving like understanding at all. It is not just another feature of the model. It is the point at which the model openly admits that it no longer knows what it is talking about. In everyday language, a singularity sounds like a thing, a point, a moment, something real and concrete. In physics, however, a singularity is not an object that exists in the universe. It is a mathematical signal. It appears when equations produce infinite values for physical quantities such as density, temperature, or curvature. When this happens, it is not usually taken as a literal description of reality. It is taken as a warning sign that the theory being used has reached the edge of its validity. This distinction is crucial because much confusion about the Big Bang arises from treating the singularity as a real event rather than as a breakdown in description. The standard cosmological equations, when run backward, lead inevitably to a state where the density of the universe becomes infinite and the size of space shrinks to zero. That is the singularity. But infinite density and zero size are not physical conditions we know how to interpret meaningfully. They are placeholders for ignorance. To understand why this happens, it helps to look at the tools being used. The Big Bang model relies on general relativity to describe how space and time evolve. General relativity is a classical theory. It treats space-time as a smooth, continuous fabric. Matter and energy curve that fabric, and the curvature tells matter how to move. This framework has been tested extensively and works extremely well across a wide range of conditions. However, general relativity does not include quantum mechanics. Quantum theory governs the behavior of matter and energy at very small scales. It introduces uncertainty, discreteness, and fluctuations that have no place in a purely smooth space-time. Under ordinary conditions, the effects of quantum mechanics on space-time itself are negligible. Space can be treated as smooth without noticeable error. In the early universe, this is no longer true. When densities become enormous and distances become extremely small, quantum effects cannot be ignored. Energy fluctuates violently. The notion of a well-defined geometry begins to break down. Trying to describe this regime using only general relativity is like trying to describe the motion of individual atoms using the physics of solid steel beams. The tool is simply not designed for the task. This mismatch is what produces the singularity. The equations are being pushed into a regime where their assumptions no longer hold. The appearance of infinity is not a discovery about reality. It is a confession of limitation. This pattern is not unique to cosmology. It has appeared before in the history of physics. In classical electromagnetism, calculations involving point charges led to infinite self-energies. These infinities were not accepted as real. They signaled that the theory was incomplete. Quantum electrodynamics eventually provided a framework that resolved these issues through renormalization and deeper structure. Similarly, in classical descriptions of atoms, electrons spiraling into nuclei would produce singular behavior. The atom should collapse instantly. It does not. Quantum mechanics replaced that picture with one that eliminated the singularity entirely. The infinities disappeared not because reality was infinite, but because the description had changed. From this perspective, the singularity associated with the Big Bang looks less like a physical beginning and more like a placeholder for new physics. Most physicists interpret it this way. They do not believe the universe literally reached infinite density. They believe our equations stopped making sense. This raises an important question. If the singularity is not real, then what replaces it? What actually happened when the universe was extremely young? The honest answer is that we do not yet know. There is no complete, experimentally confirmed theory of quantum gravity. There is no framework that successfully combines the smooth geometry of space-time with the probabilistic nature of quantum mechanics in a way that has been tested under cosmological conditions. Without such a theory, any description of the earliest moments remains speculative. Several approaches exist. String theory suggests that fundamental objects are not points, but extended entities, which could smooth out infinities. Loop quantum gravity proposes that space itself is quantized, made of discrete units that prevent infinite compression. Other approaches explore causal sets, emergent space-time, or entirely new mathematical structures. Each of these ideas offers ways to avoid singularities. In many of them, the Big Bang singularity is replaced by a bounce, a transition, or a phase change. The universe does not begin from nothing. It moves from one state to another, but none of these proposals has yet been confirmed by observation. They are active areas of research, not established conclusions. The presence of the singularity also exposes a deeper issue. Our current physics is built from theories that work extraordinarily well in their own domains but resist unification. General relativity governs the large-scale structure of space-time. Quantum mechanics governs the small-scale behavior of matter and energy. Each is internally consistent. Together, they clash. The Big Bang singularity sits precisely at the intersection of these domains. It is the place where both theories must apply simultaneously, and where neither can operate alone. That is why it is such a persistent problem. It is not a flaw in cosmology alone. It is a symptom of a deeper fracture in our understanding of nature. This fracture has consequences beyond the technical. It affects how confident we can be in statements about the universe's origin. When popular explanations say that the universe began at a singularity, they're often compressing a complex situation into a misleading phrase. What they really mean is that our current models cannot describe earlier conditions reliably. This nuance is easy to lose. Singularities make for dramatic storytelling. They sound like definitive beginnings, sharp edges where everything starts. In reality, they are more like fog banks. You can sail toward them, charting your course with confidence until suddenly the landmarks vanish. Beyond that point, the map no longer helps. The limits of our physics also shape the debate about whether the Big Bang could be wrong. If the theory predicts a singularity and singularities are signs of failure, does that mean the theory is wrong? Not necessarily. It means the theory is incomplete. Most successful scientific theories are incomplete. Newtonian mechanics does not fail because it cannot describe black holes. It fails only when used outside its domain of validity. Within that domain, it remains extraordinarily useful. Similarly, the Big Bang model works extremely well for describing the universe after a certain early time. Its failure to describe earlier conditions does not negate its successes. This is a subtle point, but an important one. Scientific theories are not judged by whether they explain everything. They are judged by whether they explain something well, and whether they can be improved or replaced when they reach their limits. The singularity marks such a limit. It tells us where improvement is needed, not where everything collapses. There is also a psychological dimension to this discomfort. Singularities feel unsettling because they represent absolute limits. Humans tend to resist the idea that there are questions that cannot yet be answered. We prefer open doors to closed ones. The singularity looks like a closed door, but in science, closed doors often mark the boundary between one era of understanding and the next. They are invitations rather than conclusions. The fact that we can identify the problem so precisely is itself a sign of progress. It is also worth noting that the singularity problem is not unique to the Big Bang. Black holes, as described by general relativity, also contain singularities. At their centers, densities and curvatures become infinite. Again, most physicists do not believe these infinities exist physically. They believe that quantum gravity effects intervene and change the picture. This parallel is important. If singularities in black holes are taken as signs of incomplete description rather than literal features, consistency suggests treating the Big Bang singularity the same way. In both cases, the theory points beyond itself. The limits of our physics are therefore not a failure of cosmology alone. They are part of a broader story about how knowledge advances. We build models that work, we discover where they fail, and we search for deeper frameworks that incorporate the old ones as approximations. As you listen to this, you may notice that the question has shifted. It is no longer simply whether the Big Bang is right or wrong. It is whether it is complete, and completeness is a much higher standard. Recognizing the problem of singularity reframes the entire discussion. It suggests that the Big Bang is best understood as a description of a phase in the universe's history, not as the final word on its origin. It suggests that whatever came before, or whatever replaces the singularity, lies in a regime we have not yet mastered. This does not diminish the achievements of modern cosmology. It places them in context. The universe's expansion, the cosmic microwave background, the formation of structure, all of these remain robustly explained. What remains uncertain is how far back those explanations can be trusted. This awareness becomes increasingly important when scientists examine observations that do not fit neatly into the standard picture, or when they propose alternative models. They are not rejecting the Big Bang out of hand. They are probing its limits. For a theory that has explained as much as the Big Bang framework has, it is easy to assume that the picture it paints must be smooth and complete. From a distance, it often looks that way. Expansion explains redshift. A hot early phase explains background radiation. Simple physics explains the abundance of light elements. When these successes are listed together, the impression is one of remarkable coherence. But when scientists look closely, not from a distance but up close, certain details begin to feel uneasy, not broken, not obviously wrong, but slightly misaligned. These are not dramatic contradictions that overthrow the entire framework. They are small tensions, persistent puzzles, places where observation and theory do not quite settle into the same shape. In science, these are often the most interesting places. One of the most discussed cracks in the picture involves the rate at which the universe is expanding today. This rate is known as the Hubble constant, and measuring it sounds at first like a straightforward task. Observe distant galaxies, determine how fast they are moving away, measure their distances and calculate the relationship. In practice, it turns out to be anything but simple. What makes this situation uncomfortable is not that the Hubble constant is hard to measure. It is that different methods of measuring it give different answers. When astronomers infer the expansion rate by looking at the cosmic microwave background and extrapolating forward using the standard cosmological model, they get one value. When they measure distances and motions of relatively nearby galaxies directly, they get another. The difference is not trivial. It is larger than the estimated uncertainties. It has persisted despite improved data and refined analysis. This discrepancy is known as the Hubble tension, and it has become one of the most closely watched issues in modern cosmology. There are several possible explanations. One is that one or more measurement methods contain subtle, unrecognized errors. Another is that the standard cosmological model is missing something, perhaps a new form of energy, or a modification to known physics. The uncomfortable part is that no explanation has yet resolved the tension cleanly. This does not mean the Big Bang theory is wrong, but it does suggest that the simple picture of expansion may be incomplete. If the universe's expansion history is not fully captured by current assumptions, then our reconstruction of its early behavior may need adjustment as well. Another area where observations raise quiet questions involves the large-scale structure of the universe. According to the standard model, matter clumped gradually over time. Small density fluctuations in the early universe grew under gravity, eventually forming galaxies, clusters, and filaments. On average, this process works well. Simulations based on the Big Bang framework reproduce many features of the observed cosmic web. Yet, when astronomers examine specific details, some structures appear unexpectedly large or unexpectedly organized. There are vast regions with fewer galaxies than expected, and immense alignments that seem unlikely under random initial conditions. Individually, these features may be statistical flukes. Collectively, they invite closer scrutiny. Cosmologists are careful here. The universe is large, and rare patterns are bound to occur somewhere. The challenge is distinguishing between genuine anomalies and the natural extremes of a probabilistic distribution. Still, the fact that such questions continue to arise reminds us that the picture is not as clean as simple summaries suggest. The cosmic microwave background itself, often described as one of the Big Bang's strongest pillars, contains its own set of oddities. On large scales, the background radiation is remarkably uniform. On smaller scales, tiny fluctuations carry information about early density variations. This pattern fits theoretical expectations extremely well. But when scientists analyze the largest angular scales, subtle anomalies appear. Certain temperature variations seem aligned in ways that are difficult to explain. Some regions appear slightly colder or warmer than expected. The overall distribution is still consistent with a Big Bang origin, but these features have resisted simple explanation. Again, none of this amounts to a decisive refutation. The anomalies could be statistical accidents, artifacts of data processing, or remnants of foreground contamination, yet they persist across multiple datasets and analyses, enough to keep the conversation alive. Another crack in the picture comes from the nature of dark matter and dark energy. These components are not minor adjustments. According to the standard cosmological model, ordinary matter accounts for only a small fraction of the universe's total energy budget. The rest is attributed to dark matter, which influences structure formation, and dark energy, which drives accelerated expansion. These entities are not directly observed. Their existence is inferred from gravitational effects and cosmic dynamics. This inference is robust in the sense that something must be causing the observed behavior. But what that something is remains unknown. The uncomfortable aspect is not just that we do not know what dark matter and dark energy are, it is that the Big Bang framework relies on them heavily. Without dark matter, galaxies would not form as observed. Without dark energy, the expansion history would look very different. Some researchers have explored alternatives such as modifications to gravity itself. These ideas attempt to explain observations without invoking unseen components. So far, None has matched the success of the Standard Model across all scales, but their very existence reflects a sense that relying so heavily on unknown ingredients leaves the picture feeling provisional. There is also the issue of early structure formation. Observations have revealed massive galaxies and quasars existing earlier in cosmic history than some models predicted. Forming such objects requires time, matter, and efficient processes. Their early appearance suggests that structure formation may have proceeded faster or more efficiently than expected. Adjustments can be made to accommodate these observations. Parameters can be tuned, feedback processes can be revised, but each adjustment adds complexity. The core framework remains intact, yet the edges become more intricate. Another subtle tension involves the uniformity of the universe. Inflation was introduced to explain why distant regions of the universe share similar properties, despite appearing causally disconnected. Inflation works well in many respects, but it raises questions about its own initial conditions and dynamics. Different inflationary models predict slightly different patterns in the cosmic microwave background. As measurements become more precise, some models are favoured over others. So far, no single inflationary scenario has emerged as uniquely compelling. The broad idea remains plausible, but its details remain unsettled. This uncertainty does not undermine the Big Bang itself, but it does weaken claims that the early universe is fully understood. The picture becomes layered, with well-supported features resting atop less certain foundations. There are also observational puzzles closer to home. Measurements of galaxy rotation curves and gravitational lensing reveal discrepancies between visible matter and gravitational effects. Dark matter accounts for these discrepancies within the Standard Model, but the exact distribution and behaviour of dark matter remain uncertain. Some small-scale observations do not match predictions perfectly. For example, the number of small satellite galaxies around larger galaxies appears lower than expected in some simulations. This issue, known as the missing satellites problem, has been mitigated by improved modelling, but it illustrates how details can challenge assumptions. Taken together, these cracks do not form a single fault line. They are scattered, varied, and often subtle. Each has plausible explanations. None demands abandonment of the Big Bang framework, but they collectively suggest that the story is still being refined. In science, this is not unusual. Theories often work extremely well at a certain level while struggling at the margins. The margins are where progress happens. They are where new ideas are tested, where assumptions are questioned, and where deeper understanding can emerge. It is also important to distinguish between cracks in the Big Bang theory itself and cracks in the broader standard cosmological model. The Big Bang refers primarily to the hot, dense early phase and subsequent expansion. The Standard Model includes additional assumptions about matter content, dark energy, and inflation. Some tensions may point to modifications in those additions rather than to the core idea of expansion. Public discussions often blur this distinction. When people say the Big Bang is in trouble, they may be referring to issues with dark energy, inflation, or structure formation, rather than with the basic expansion history. Precision matters here, because different problems suggest different kinds of solutions. As you reflect on these observational tensions, you may notice a pattern. The Big Bang framework is rarely contradicted outright. Instead, it is surrounded by questions that push its boundaries. These questions do not shout, they whisper. They ask whether certain assumptions are as secure as we think, whether certain parameters are truly fundamental, and whether deeper principles remain hidden. This kind of situation can persist for a long time in science. Sometimes tensions resolve as data improves. Sometimes they accumulate until a conceptual shift becomes unavoidable. It is not always clear which path will be taken. For now, the Big Bang remains the best available description of the universe's early evolution. But it is not beyond challenge. Its success does not guarantee its completeness. The cracks in the picture remind us that understanding the universe is an ongoing process, not a finished achievement. When the standard picture of the universe reaches its edges, when expansion leads backward to a singularity and observation meets horizons it cannot cross, it is almost inevitable that alternative ideas begin to appear. These ideas do not usually arise from a desire to overturn everything that came before. More often, they grow out of an attempt to soften the sharpest limits of the existing framework, to replace abrupt boundaries with continuity, and to answer questions that refuse to go away. What unites many of these alternatives is a shared discomfort with the notion of an absolute beginning. Not because a beginning is philosophically unacceptable, but because the physics surrounding it feels incomplete. Singularities, infinities, and unexplained initial conditions are not endpoints scientists are usually content to accept. They are markers that something deeper may be waiting underneath. One broad family of ideas replaces the idea of a single beginning with the idea of a bounce. In these models, the universe does not emerge from nothing. Instead, it transitions from a previous state. The expansion we observe today is the aftermath of a contraction that came before. In a bouncing universe, cosmic history extends further back than the Big Bang. The universe may have been shrinking for a long time, becoming denser and hotter, until some mechanism halted the contraction and reversed it. That reversal, the bounce, takes the place of the singularity. The appeal of such models is straightforward. If the universe never reaches infinite density, then the singularity problem disappears. Instead of equations blowing up, physical processes intervene. Quantum effects, repulsive forces, or new states of matter prevent collapse beyond a certain point. Several versions of bouncing cosmologies exist. Some arise from loop quantum gravity, where space itself is quantized. In these models, there is a smallest possible unit of volume. Compression beyond that limit is impossible, so contraction naturally gives way to expansion. The universe rebounds not because of an explosion, but because the fabric of space resists further squeezing. Other bounce models emerge from modified gravity theories, where the equations governing space-time behave differently at high densities. In these scenarios, gravity may become repulsive under extreme conditions, halting collapse and initiating expansion. While these ideas are mathematically consistent within their own frameworks, they face significant challenges. One of the hardest is matching observational data successfully as the standard Big Bang model does. Any viable alternative must reproduce the cosmic microwave background, the distribution of galaxies, and the observed expansion history with comparable accuracy. Another difficulty involves entropy. If the universe contracts and then expands, what happens to disorder? In most physical processes, entropy increases. A contracting phase would need to manage entropy carefully to avoid contradictions with the observed low-entropy early universe. Some models address this by proposing that entropy is reset or diluted during the bounce. Others suggest that entropy behaves differently in cosmological contexts. Closely related to bouncing universes are cyclic models. In these pictures, the universe does not experience a single bounce, but many. Expansion follows contraction, which follows expansion, repeating over immense timescales. Each cycle may last trillions of years. The universe has no beginning and no end, only transitions. Cyclic cosmologies have a long history. Even before modern physics, some philosophers imagined an eternal universe that renews itself endlessly. Modern cyclic models attempt to ground this intuition in mathematics and observation. One influential version proposes that the universe undergoes phases dominated by different forms of energy. Expansion slows, reverses, contracts, and then bounces again. Another version, sometimes called conformal cyclic cosmology, suggests that the far future of one universe becomes mathematically equivalent to the Big Bang of the next. These models offer intriguing solutions to the beginning problem. If the universe has always existed in some form, then there is no need to explain why it suddenly appeared. The question shifts from origin to dynamics. Why does the universe cycle the way it does? What governs the transitions? However, cyclic models face their own obstacles. Maintaining consistency across cycles without accumulating inconsistencies is difficult. small deviations can compound over time. Entropy again poses a major challenge. If disorder increases with each cycle, the universe should eventually reach a state where cycles are impossible. Some cyclic models attempt to avoid this by proposing mechanisms that reset entropy between cycles. Others argue that entropy behaves differently on cosmic scales. These ideas are still under active debate. Another broad alternative involves eternal cosmologies that do not rely on cycles or bounces, but on ongoing processes without a global beginning. In these models, the universe may be eternally inflating, constantly generating new regions that look like Big Bang universes from the inside. Eternal inflation is not a rejection of the Big Bang so much as an extension of inflationary theory. In this picture, inflation never completely ends everywhere. While it stops locally, producing regions like our observable universe, it continues elsewhere. Each region emerges with its own expansion history, physical properties, and apparent beginning. From within one such region, the universe appears to have begun with a hot, dense phase. From the broader perspective, that beginning is local rather than absolute. There is no single starting point for the entire cosmos. This idea naturally leads to multiverse scenarios. If many regions form under slightly different conditions, then physical constants may vary from one region to another. The universe we observe would be one realization among many. Eternal inflation has the advantage of arising from mechanisms already proposed to explain early universe behavior. It also provides a possible explanation for why physical constants appear finely tuned for complexity. In a multiverse, observers exist only in regions where conditions allow them to exist. At the same time, this framework raises serious questions about testability. If other regions of the multiverse are causally disconnected from us, how can their existence be confirmed or falsified? Some argue that indirect evidence may be possible. Others worry that the theory drifts too far from empirical grounding. There are also eternal models that do not rely on inflation. Some propose steady-state-like universes where large-scale properties remain statistically constant over time, even though local regions evolve. These ideas differ from earlier steady-state theories by incorporating modern observations and avoiding continuous matter creation in its original form. What all these alternatives share is an attempt to replace a sharp beginning with a broader context. They aim to answer the question the Big Bang theory does not. What, if anything, lies beyond its starting point? It is important to notice that proposing alternatives does not mean discarding the evidence that supports the Big Bang. Most of these models still include a hot, dense, early phase resembling the Big Bang. They reinterpret it rather than deny it. The cosmic microwave background, light element abundances, and large-scale structure still need explanation. In that sense, the Big Bang may survive as a description of a phase rather than an origin. The question becomes not whether the Big Bang happened, but what kind of event it was within a larger story. Critics of alternative models often point out that adding new structures, cycles, or universes increases complexity. Occam's razor, the principle that simpler explanations are preferable, is sometimes invoked. Why multiply universes or cosmic phases when a single beginning suffices? Supporters respond that simplicity is not the same as truth. A theory that hides unanswered questions behind a singularity may appear simple, but that simplicity may be deceptive. A more complex model that resolves deep inconsistencies may ultimately be more satisfying. Another consideration is how science progresses. New ideas often appear speculative at first. They struggle to compete with established frameworks. Over time, some gain support, others fade away. The presence of many alternatives does not mean the field is confused. It means it is actively exploring its boundaries. From a broader perspective, these alternative cosmologies remind us that the universe may be stranger than any single model suggests. Our current theories are shaped by available data, mathematical tools, and human intuition. They are not guaranteed to capture the full picture. As you listen, you might notice that these alternatives vary widely in tone. Some feel conservative, extending known physics gently. Others feel radical, reimagining time, space, and causality. This diversity reflects the depth of the problem. When questions reach the foundations of reality, many paths must be explored. None of these ideas has yet displaced the standard Big Bang framework. That framework remains the most successful description of the universe's early evolution, but the existence of serious, mathematically consistent alternatives shows that the story is not closed. This matters for the original question. If the Big Bang were a complete and final explanation, alternatives would be unnecessary. The fact that they continue to be developed suggests that cosmology is still searching for a deeper understanding. The universe may have bounced, it may cycle, it may have no beginning at all in the usual sense, or the Big Bang may turn out to be the true beginning, with a singularity resolved in ways we cannot yet imagine. At this stage, honesty requires admitting that we do not know. What we do know is that the Big Bang theory, as powerful as it is, does not exhaust the possibilities. It describes what we can see and model with confidence. Beyond that lies a landscape of ideas shaped by both caution and imagination. What if the universe is not only stranger in its past, but older than we think? What if the timeline itself is longer, more layered, or more ambiguous than the neat number we often hear repeated? When people talk about the age of the universe, they often speak with a surprising degree of confidence. Around 13.8 billion years, give or take a few tens of millions. It sounds precise, almost comforting, as though the universe has a clearly printed birth certificate tucked away somewhere in the cosmic archives. This number appears in textbooks, documentaries, articles, and casual conversations, usually without much hesitation. And yet, when you look closely at how that number is obtained and what assumptions it rests upon, the certainty begins to soften. The age of the universe is not something we measure directly. It is something we infer. It is the result of models layered on top of observations, interpretations stacked on top of equations. Change the assumptions, even slightly, and the age can shift. This does not mean the number is meaningless. It means it is conditional. The commonly cited age of the universe comes from combining measurements of cosmic expansion with a specific cosmological model. In simple terms, astronomers observe how fast the universe is expanding today, and use that information, along with assumptions about how the expansion rate has changed over time, to calculate how long it would take to reach the current state from a much denser one. This is similar to estimating how long a car has been travelling based on its current speed and an assumed acceleration history. If you know how fast it is going now and how it's sped up or slowed down along the way, you can estimate when the journey began. But if your assumptions about acceleration are off, even slightly, your estimate of the starting time will be too. In cosmology, those assumptions are encoded in the standard model, including the influence of dark matter, dark energy, and the overall geometry of space. The age of 13.8 billion years is not a raw observational fact. It is the age implied by this particular model fitting this particular set of data. One reason this matters is that there are independent ways of estimating cosmic age that do not always line up perfectly. Astronomers can estimate the ages of the oldest stars, the oldest star clusters, and the earliest galaxies. These objects act as cosmic clocks. If a star is 13 billion years old, the universe must be at least that old. For a long time, there were mild tensions between stellar age estimates and cosmological age estimates. At times, the oldest stars appeared to be almost as old as the universe itself, leaving very little room for error. Improvements in measurements and models have eased these tensions, but they have not eliminated uncertainty entirely. More recently, the tension surrounding the expansion rate of the universe has reopened questions about age. As discussed earlier, different methods of measuring the expansion rate yield different values. A faster expansion rate today implies a younger universe. A slower rate implies an older one. If the universe is expanding faster than the standard model predicts, then extrapolating backward leads to a shorter timeline. If it is expanding more slowly, the timeline stretches. The current disagreement between measurement methods therefore has direct implications for cosmic age. Some proposed solutions to this tension involve modifying the early expansion history of the universe. These modifications can subtly change the inferred age. In some scenarios, the universe could be older than the standard estimate, even while still matching most observations. There is also a deeper question hidden beneath these calculations. What does it even mean to say that the universe has an age? Age, as we usually understand it, assumes a beginning point. It assumes a clock that started ticking at a definite moment. But if the Big Bang was not an absolute beginning, but rather a transitional phase, then the age we calculate may only apply to the current expansion phase, not to the universe as a whole. In bouncing or cyclic models, for example, the universe could be vastly older than 13.8 billion years. The expansion we observe would represent only the most recent cycle or rebound. From our perspective, looking backward, everything appears to originate from a hot, dense state. But that state would not be the first. In such a scenario, asking for the age of the universe is like asking for the age of a wave on the ocean. The wave has a beginning and an end, but the ocean itself does not begin with that wave. The age we measure belongs to the pattern, not to the underlying system. Even within inflationary models, similar ambiguities arise. If inflation is eternal to the past, or if it operates within a broader timeless framework, then the Big Bang-like phase we observe may not mark the beginning of all existence. It may mark the beginning of our observable region's history. In that case, the universe could be effectively older than any age we can assign using current observations. The number 13.8 billion years would describe the time since our region emerged from inflation into a hot, expanding phase, not the age of the entire cosmos. There is also the possibility that time itself behaves differently at very early stages. Some approaches to quantum gravity suggest that time may emerge gradually, rather than existing fully formed from the outset. If this is the case, then the concept of age becomes fuzzy near the beginning. If time emerges from more fundamental processes, asking how old the universe is may be like asking how old a shadow is relative to the object casting it. The question may have meaning only after certain conditions are met. These ideas are speculative, but they illustrate an important point. The age of the universe is not a single, unquestionable fact. It is a model-dependent quantity, meaningful within a particular framework and less so outside it. This becomes especially relevant when people ask whether the Big Bang could be wrong. Often, what they mean is not that the universe was never hot and dense, but that the timeline we associate with that phase may not represent the full story. The universe could have a deeper past that the Big Bang model does not capture. Another way the universe could be older than we think involves changes to early expansion dynamics. If the expansion history was more complex than assumed, perhaps involving additional phases or transitions, then backward extrapolation using a simplified model could underestimate the true duration. Even small deviations in early behavior can have large effects on inferred age. Because the timeline is compressed near the beginning, uncertainties there propagate forward dramatically. Observationally, probing these early phases is extremely difficult. The cosmic microwave background provides a snapshot of the universe when it was about 380,000 years old. Everything before that is inferred indirectly. While those inferences are grounded in well-tested physics, they are still extrapolations. This is not a flaw unique to cosmology. In geology, the age of the Earth is inferred using radioactive decay models. In biology, evolutionary timelines are inferred from genetic divergence. In each case, the estimates are robust but conditional. They depend on assumptions about processes over time. Cosmology operates under even more extreme conditions, dealing with energies and scales far beyond anything we can reproduce experimentally. That makes humility especially important. It is also worth noticing how language shapes perception here. Saying the universe is 13.8 billion years old sounds definitive. Saying the observable universe has been expanding for approximately 13.8 billion years under the assumptions of the standard cosmological model sounds less catchy, but far more accurate. Public discourse tends to favour the first phrasing. Scientific discourse prefers the second. The gap between them can create confusion, especially when new data challenge existing assumptions. None of this means that the universe is definitely older than we think. It means that the age we assign is provisional. It reflects our best current understanding, not an absolute truth guaranteed to survive future discoveries unchanged. As our measurements improve and our theories evolve, the number may shift. It may increase slightly, it may decrease slightly, or it may turn out that the question itself needs to be reframed. For listeners, this realization can be strangely calming. It removes the pressure to treat cosmological numbers as sacred. It invites curiosity rather than anxiety. The universe does not become less impressive if it is older, younger, or more complex than we imagine. If anything, it becomes more interesting. There is a quiet but important shift that happens when a question is framed slightly differently. Instead of asking whether the Big Bang is right or wrong, the focus turns toward whether it is finished. That change may sound subtle, but it reshapes the entire conversation. Wrong suggests failure. Incomplete suggests work in progress. Science, almost by definition, lives far more comfortably with the second than the first. To see why this distinction matters, it helps to step back and consider how scientific theories actually function. A theory in science is not a declaration of ultimate truth. It is a structured way of organizing observations, making predictions, and connecting disparate facts into a coherent picture. Theories are judged not by whether they answer every conceivable question, but by whether they explain what they claim to explain within a clearly defined domain. By that standard, the Big Bang theory has been remarkably successful. It explains why distant galaxies are receding from one another. It explains why the universe was hotter and denser in the past. It explains the presence and properties of the cosmic microwave background. It explains the relative abundance of the lightest elements. These are not minor achievements. They cover the large-scale behavior of the universe over billions of years. Yet none of these successes require the Big Bang to be a complete description of cosmic history. They require it only to be an accurate description of a particular phase. Confusion arises when that phase is treated as the entire story, rather than as one chapter within a larger unfinished framework. The idea of incompleteness is not an insult in physics. It is an expectation. Newtonian mechanics is incomplete. It cannot describe relativistic speeds or quantum effects. That does not make it wrong in everyday contexts. It makes it limited. Quantum mechanics is incomplete. It does not incorporate gravity. General relativity is incomplete. It does not include quantum uncertainty. Each theory remains indispensable within its proper scope. In this light, asking whether the Big Bang is incomplete is almost redundant. Of course it is. The more interesting question is where that incompleteness lies and what it tells us about the structure of reality. One place where incompleteness becomes obvious is at the earliest times. The Big Bang model describes how the universe evolves from a hot, dense state onward. It does not provide a well-defined account of how that state arose. The appearance of a singularity marks a breakdown, not a conclusion. That alone is enough to say the theory is not complete in the deepest sense. Another place where incompleteness shows itself is in the reliance on unknown components. Dark matter and dark energy are not minor footnotes. Together they dominate the universe's energy budget. Their existence is inferred from strong evidence, but their nature remains mysterious. A theory that depends so heavily on entities it cannot yet explain is, by definition, provisional. This does not mean dark matter and dark energy are imaginary. It means that our description of the universe is missing key pieces. Whether those pieces will turn out to be new particles, new fields, or modifications of existing laws is still an open question. The same can be said of inflation. Inflation solves several important problems in early universe cosmology, but it introduces its own unanswered questions. What drove inflation? Why did it last as long as it did? Why did it end in the way that produced our observed universe? Inflation works as an effective description, but its underlying mechanism remains uncertain. These gaps do not undermine the Big Bang, they surround it. Another reason the theory feels incomplete is that it treats certain conditions as given rather than explained. The initial uniformity of the universe, the specific spectrum of fluctuations, the low entropy at early times, all are inputs rather than outputs. The theory accepts them and shows how they evolve, but it does not explain why they were that way to begin with. This is often where philosophical discomfort creeps in. Why these laws? Why these constants? Why these initial conditions? The Big Bang model does not pretend to answer such questions. They lie outside its design. Expecting it to do so is like expecting a map to explain why the terrain exists. In public discourse, incompleteness is often mistaken for weakness. There is an assumption that if the theory does not answer everything, it must be on shaky ground. In science, the opposite is often true. Theories that clearly mark their limits tend to be the most robust. They invite refinement rather than collapse. This perspective also helps clarify why alternatives to the Big Bang are not necessarily competitors in the usual sense. Many alternative cosmologies retain the Big Bang as a phase within a broader structure. They do not discard its successes, they reinterpret them. For example, in a bouncing universe, the Big Bang corresponds to the transition from contraction to expansion. In eternal inflation, it marks the local beginning of our observable region. In cyclic models, it represents one turn of a much larger cosmic process. In each case, the Big Bang is incomplete, but not wrong. This reframing changes the emotional tone of the discussion. Instead of defending the Big Bang against every criticism, scientists can ask which parts of it are likely to survive deeper theories and which parts may be revised or replaced. History suggests that the broad idea of expansion from a hotter past is likely to endure, even if the details of the earliest moments change significantly. Another way to think about incompleteness is to ask how the Big Bang would look if discovered today for the first time. Would it be presented as a final explanation, or as a highly successful model with known limitations? Almost certainly the latter. Much of the confusion arises from how the theory has been communicated over time, not from what it actually claims. The word beginning carries heavy baggage. It suggests finality, absoluteness, and closure. In practice, the Big Bang describes a boundary of applicability, not a metaphysical origin. Treating it as incomplete rather than wrong aligns better with how physicists actually use it. There is also a deeper lesson here about how science handles ultimate questions. Some questions may not have answers in the form we expect. Asking what caused the Big Bang may presuppose a type of explanation that physics is not equipped to provide. Causation, as we experience it, depends on time. If time itself emerges from deeper processes, then causal language may need to be rethought. This does not mean the question is meaningless. It means the answer may not resemble ordinary explanations. Recognizing incompleteness allows space for that possibility without forcing premature conclusions. It is also worth noticing how often scientific revolutions involve reframing rather than rejection. Relativity did not declare Newton completely wrong. It showed that Newton's laws were approximations valid under certain conditions. Quantum mechanics did not erase classical physics. It explained why classical behavior emerges from deeper rules. In that sense, whatever replaces or extends the Big Bang is likely to include it as a limiting case. The expansion history, the cosmic background radiation, the growth of structure, these features are unlikely to vanish from future theories. They're too well supported by evidence. What may change is how those features are embedded in a larger picture. The earliest moments may be described differently. Time may behave differently. Space itself may have a discrete structure. the notion of a beginning may dissolve into something less absolute. Seeing the Big Bang as incomplete also helps diffuse the idea that questioning it is somehow anti-scientific. On the contrary, probing incompleteness is how science advances. Every major breakthrough has emerged from identifying where existing theories stop working smoothly. This perspective encourages a quieter, more patient kind of curiosity. Instead of demanding final answers, it allows questions to remain open. Instead of framing uncertainty as failure, it treats it as a guide. As you listen to this, you may notice that the universe feels no less real or stable when its description is incomplete. In fact, it may feel more alive, more dynamic, more open to discovery. A finished universe is static. An unfinished one invites exploration. The Big Bang, then, can be understood as a remarkably successful description of a vast stretch of cosmic history, paired with a clear acknowledgement of its limits. It tells us how the universe expanded, cooled, and structured itself. It does not tell us everything about why or from what deeper processes those events emerged. Holding this balance is not easy, especially in a culture that prefers definitive answers, but it is closer to how science actually operates, moving forward through approximation, revision, and deepening insight. With that shift in perspective, the next question naturally arises. If scientific theories are allowed to be incomplete without being discarded, how do they change over time without everything falling apart? Stability is not usually the first word that comes to mind when people imagine scientific change. The popular image is far more dramatic. Old ideas collapse, new ones sweep in, textbooks are rewritten overnight. Everything we thought we knew turns out to be wrong. It is a compelling picture, but it bears very little resemblance to how science actually evolves, especially in fields like cosmology, where theories are built slowly, tested indirectly, and refined across generations. Understanding how scientific theories change without everything falling apart is essential for making sense of the ongoing conversation about the Big Bang. Without that understanding, any revision can feel like a threat, any uncertainty like a crack in the foundation. With it, change looks less like destruction and more like careful renovation. At the heart of this process is a simple but often misunderstood idea. Scientific theories are not fragile structures held together by belief. They are resilient frameworks anchored by evidence. When they change, they rarely shatter. They bend, stretch, and absorb new information, sometimes transforming in shape while retaining their core function. A useful place to begin is with how theories are built in the first place. A scientific theory does not emerge fully formed. It grows from patterns observed in data, from regularities that demand explanation. Early versions are often rough, incomplete, and limited in scope. Over time, as measurements improve and new phenomena are discovered, the theory is adjusted to accommodate them. This adjustment process is not arbitrary. It is constrained by what already works. A theory that successfully explains a wide range of observations cannot simply be discarded without replacing those explanations. Any new theory must either reproduce the old theory's successes or explain why those successes appeared to hold under certain conditions. This is why scientific revolutions are usually additive rather than subtractive. When relativity replaced Newtonian gravity, it did not invalidate Newton's laws in everyday situations. It explained why Newton's laws work so well at low speeds and weak gravitational fields, while revealing their limitations at extreme scales. Engineers still use Newtonian physics every day. Its domain did not disappear, it was clarified. The same pattern appears in quantum mechanics. Classical physics did not become useless when quantum theory arrived. It became understood as an approximation that emerges from deeper rules when systems are large and energies are moderate. The world did not fall apart. It became layered. Cosmology follows this same pattern. The Big Bang theory did not emerge by destroying earlier astronomy. It built on it. Observations of stars, galaxies, and motion remained valid. What changed was the interpretation of large-scale structure and history. When people worry that questioning the Big Bang might cause everything to collapse, they are often imagining science as a single rigid story. In reality, it is a collection of interconnected models, each with its own range of validity. Changing one part does not automatically destabilize the rest. This resilience comes from redundancy. The Big Bang framework is supported by multiple independent lines of evidence. Expansion is seen in galaxy redshifts. Early heat is recorded in background radiation. Nuclear processes are reflected in elemental abundances. These facts do not vanish if the theory is refined. They must be explained by whatever framework replaces or extends it. Because of this, scientific change is usually conservative in the best sense of the word. It preserves what works. It modifies what does not. It rarely starts from zero. Another important aspect of stability is the role of uncertainty. Contrary to popular belief, uncertainty does not weaken a theory. Unacknowledged uncertainty does. When scientists explicitly identify the limits of a model, they create space for growth without crisis. The Big Bang theory includes such limits. It does not claim to describe the universe at all times and scales. It does not claim to explain the ultimate origin of physical law. These omissions are not flaws, they are boundaries. When new observations press against those boundaries, scientists do not panic. They ask whether the boundary can be pushed outward, or whether a deeper framework is needed. This mindset prevents collapse because it anticipates incompleteness from the beginning. Another stabilizing factor is the way theories are embedded in practice. Cosmology is not just a set of ideas, it is a working discipline. Observations are planned, instruments are built, data are analysed, and predictions are tested. A theory that works well in practice acquires a kind of inertia. It is not easily displaced by speculation alone. This is why alternative cosmologies, no matter how elegant, must do more than propose new narratives. They must match the predictive power of the existing framework. They must account for the same data at least as well. Until they do, the standard model remains in place, even if it is known to be incomplete. The process resembles architectural engineering more than demolition. You do not tear down a bridge because you discover that its design can be improved. You reinforce it, adjust it, and sometimes rebuild sections while keeping it operational. There is also an important social dimension to scientific stability. Science is not done by isolated individuals working in conceptual vacuum. It is done by communities that share methods, standards, and expectations. These communities change slowly, not because they resist truth, but because coordination matters. A radical change must be communicated, tested, debated, and reproduced across many independent groups. This takes time. During that time, old and new ideas coexist. This coexistence can look messy from the outside, but it is part of what keeps science grounded. This gradualism is often misinterpreted as stubbornness. In reality, it is caution. Extraordinary claims require extraordinary evidence, not because scientists are dogmatic, but because they are responsible for maintaining coherence across vast bodies of knowledge. Another reason theories do not fall apart easily is that they are modular. Different components address different questions. In cosmology, expansion history, structure formation, particle physics, and gravity are related but not identical domains. Adjusting one does not require rewriting all the others. For example, revising our understanding of dark energy does not invalidate stellar evolution models. Modifying inflationary theory does not change how light travels through space today. This compartmentalization allows progress to occur locally without global collapse. It also allows theories to be tested incrementally. Predictions can be refined, parameters can be adjusted, new observations can be incorporated. At no point is everything on the table at once. This is why the idea of the Big Bang being incomplete does not alarm cosmologists. It is expected. What would be alarming is a theory that claimed to explain everything perfectly, leaving no room for further inquiry. In fact, The history of science suggests that theories which appear too complete often hide unresolved assumptions. These assumptions eventually surface as contradictions or anomalies. A theory that openly acknowledges its limits is healthier. This perspective also helps explain why public debates about science can feel more dramatic than professional ones. Outside the scientific community, theories are often treated as beliefs rather than tools. Changing a belief feels like losing ground. Refining a tool feels like progress. When people hear that cosmologists are questioning aspects of the Big Bang, they may imagine chaos. Inside the field, it feels more like routine maintenance. The universe has not become unstable because our descriptions evolve. The universe does not care what we think about it. Our models change because they are approximations, not because reality is fragile. There is also an emotional element worth acknowledging. Humans prefer certainty, especially about fundamental questions. Knowing how everything began feels grounding. When that knowledge becomes provisional, it can feel unsettling. Science does not exist to provide comfort. It exists to describe reality as accurately as possible, even when that description resists closure. Learning to live with provisional understanding is part of engaging honestly with science. This does not mean anything goes. Constraints matter, evidence matters, mathematical consistency matters. Theories do not drift aimlessly. They are guided by what the universe reveals through observation and experiment. In cosmology, this guidance is especially indirect. We cannot recreate early universe conditions in laboratories. We infer them from faint signals and distant light. This makes caution even more important. As a result, change in cosmology is often slower and more conservative than in other fields. When change does occur, it tends to be carefully justified. Seen from this angle, the ongoing discussion about the Big Bang looks less like a crisis and more like a maturation. The theory has moved beyond its early triumphs into a phase where refinement and integration with deeper physics are required. This is a natural stage in the life of a successful theory. Early success establishes credibility. Later challenges expose limits. Those limits motivate deeper work. The Big Bang theory is currently in this second phase. Its core insights remain robust. Its boundaries are increasingly visible. That visibility is a sign of progress, not decay. As you reflect on this, it may help to release the idea that science advances through sudden revelations. Most of the time, it advances through careful adjustment, patient debate, and incremental insight. Theories change without everything falling apart because they are designed to. They are provisional by nature. They are built to be revised. This understanding sets the stage for the final shift in perspective. If the Big Bang is incomplete rather than wrong, and if scientific theories evolve without collapsing, then the real question becomes less about error and more about meaning. What does it mean for us, as observers inside the universe, to live with an origin story that is still unfinished? How does that uncertainty shape our place in the cosmos, not as a problem to be solved, but as a condition to be lived with? Somewhere beneath the equations, the observations, and the careful language of cosmology, there is a quieter question that tends to surface only after the technical debates have settled for a moment. It is not a question about expansion rates or background radiation. It is a question about perspective. If the beginning of the universe is not as clean, singular, or final as we once imagined, what does that actually change for us? At first glance, the answer might seem to be very little. Stars still burn, galaxies still drift, time still moves forward in the way we experience it. Our daily lives do not depend on whether the universe began with a singular event, a bounce, or something else entirely. And yet, when ideas about origin shift, they tend to ripple outward in subtle ways. They affect how we think about time, meaning, certainty, and our place within something vastly larger than ourselves. For a long time, the Big Bang has served as a kind of cosmic anchor. It offered a definite starting point, a moment where the story began. Even for those who did not think about it often, that beginning sat quietly in the background, giving the universe a clear direction. There was a past that led to a present, and the present moved away from a known origin. If that origin turns out to be less absolute, less final, or less singular than we thought, the anchor loosens. The universe begins to look less like a story with a first page and more like a process whose edges are harder to define. This does not remove meaning, but it changes its texture. One of the first things this shift affects is how we think about time. A universe with a sharp beginning invites us to imagine time as something that started ticking at a particular moment. Everything after that moment counts. Everything before it does not exist. This aligns neatly with how we tell stories, mark anniversaries, and measure age. If instead the Big Bang marks a transition rather than a creation, time becomes more layered. The time we measure, the time recorded in clocks and calendars, may belong only to a particular phase of cosmic history. There could be forms of time that preceded it, or structures where time behaves differently altogether. For us, this does not mean our experience of time is invalid. It means our experience is local. We live within a particular slice of cosmic history, shaped by specific physical conditions. Our clocks measure the rhythm of this slice, not necessarily the rhythm of all existence. There is something humbling in that realization. It suggests that even our most basic intuitions, like before and after, may not be universal truths, but context-dependent tools that work well within our environment. This humility extends to the idea of certainty. A clean beginning encourages the belief that the universe is, in principle, fully knowable. If we can trace everything back to a starting point, then perhaps, given enough data and computation, the entire story can be reconstructed. When the beginning becomes fuzzy, that sense of total knowability softens. There may be aspects of cosmic history that are fundamentally inaccessible, not because we have failed to discover them, but because the universe itself does not preserve that information in a retrievable way. This can feel unsettling, especially in a culture that often treats knowledge as something that accumulates endlessly. But it can also be freeing. It allows us to accept mystery without treating it as a flaw. For us as individuals, this shift can subtly change how we relate to science. Science becomes less about delivering final answers and more about mapping reliable regions within a vast unknown. The value lies not in closure, but in clarity about where clarity is possible. Another implication touches on meaning itself. When the universe is framed as having a definite beginning, it is tempting to attach significance to that moment. Origins feel important. They feel purposeful, even when described in purely physical terms. If the universe did not begin in a single decisive event, then meaning does not cluster at the start. It emerges gradually, locally, through processes rather than through a single act. Stars form, planets coalesce, life appears, consciousness arises, meaning unfolds rather than being planted at the beginning. This view aligns well with what we observe. Meaning, as we experience it, is not something handed down from the start of time. It is something constructed through relationships, memory, and awareness. A universe without a sharp beginning does not diminish that process. If anything, it emphasizes it. There is also a shift in how we think about ourselves as observers. In a universe with a clear beginning, it is tempting to imagine ourselves as late arrivals, appearing near the end of a long, predetermined sequence. Everything important happened early. We are living in the aftermath. If the universe is older, cyclic, or eternal in some sense, that framing changes. We are not late to the story. We are participants in an ongoing process that does not privilege one moment over another. This does not make us more important in a cosmic sense, but it does make our moment less derivative. We are not simply living in the fading echo of an initial event. We are embedded in a living, evolving structure that continues to generate novelty. This perspective can influence how we think about the future as well. A universe that began suddenly and is heading towards some final state can feel finite in a narrative sense. There is a beginning, and there will be an end. Our role lies somewhere in between. A universe without a clear beginning invites different kinds of futures. Cycles suggest renewal, eternal processes suggest continuity. Even scenarios involving eventual heat death take on a different tone when the past is not anchored to a single origin. For us, this can subtly affect how we think about progress, legacy, and continuity. Our actions do not sit between two absolute endpoints. They are part of a much longer, less sharply bounded flow. There is also an emotional dimension to this. Humans often look to beginnings for reassurance. Knowing where something came from can make it feel less arbitrary. When beginnings blur, the universe can feel less like a designed system and more like an emergent one. Some people find this unsettling, others find it comforting. An emergent universe does not impose meaning from the top down. It allows meaning to arise where conditions allow it, including here in conscious beings capable of reflection. This does not require abandoning awe. If anything, it deepens it. A universe that continually generates structure without a single starting command is, in its own way, more remarkable than one that began with a single decisive act. It is also worth considering how this shift affects our relationship to uncertainty. If the beginning is not fully known, and perhaps not fully knowable, then uncertainty becomes a permanent feature rather than a temporary inconvenience. Learning to live with that uncertainty is part of scientific maturity. It mirrors personal maturity as well. We do not demand complete certainty in our relationships, our identities, or our futures. We learn to navigate complexity without final answers. In this sense, cosmology becomes a mirror. How we respond to uncertainty about the universe often reflects how we respond to uncertainty in our own lives. Do we see it as a threat or as an invitation to curiosity? Another implication lies in how we teach and communicate science. If the Big Bang is incomplete rather than wrong, then science education benefits from emphasizing process over proclamation. Students learn not just what we think we know, but how that knowledge is structured, tested, and revised. This approach builds resilience. It prepares people to encounter new information without feeling that everything they learned before has been invalidated. It fosters trust in science as a method rather than as a source of final answers. For those listening quietly, perhaps late at night, these ideas do not demand action. They do not require you to change how you live tomorrow. They simply offer a different backdrop against which everyday life unfolds. You still wake up. You still rest. You still notice time passing. The universe still expands, whatever that ultimately means. The difference lies in how rigidly we hold the story of where it all began. If the beginning is not what we thought, then our place in the universe is not diminished. It is contextualized. We are part of a story that is larger, older, and less neatly packaged than we once imagined. There is something gently reassuring in that. It means we are not responsible for understanding everything. We are participants in a process that continues whether or not we have the full map. If the universe resists a single, definitive origin story, and if our theories remain open-ended, what does it mean to arrive at the end of this exploration, knowing that the story itself may never truly end? Quietly, without announcing itself, a realization tends to settle in by the time we reach the edge of this conversation. The universe we inhabit is not a solved puzzle. It is not a finished diagram with every piece locked into place. It is a system still holding back information, not out of secrecy or indifference, but because of the way it is structured, layered, and lived inside. Living inside a universe that is still keeping secrets is not a failure of science, and it is not a personal shortcoming on our part. It is a condition, one we've always lived with, even when we believed otherwise. For much of human history, the night sky felt unknowable in a very different way. Stars were distant lights with no clear explanation. Motion in the heavens was mysterious, and often interpreted through stories rather than measurements. Over time, careful observation replaced myth, and patterns replaced speculation. We learned that stars are suns, that galaxies exist beyond our own, that the universe expands. Each step forward made the cosmos feel more intelligible, and yet, with each layer of understanding, new forms of mystery appeared. The Big Bang once felt like a final answer, a moment where everything began, neat and definitive. Over time, that confidence softened. The beginning became less like a point and more like a boundary, then less like a boundary and more like a region of uncertainty. Now it feels increasingly like a question we have learned how to ask clearly, without yet knowing what a full answer would even look like. This does not mean progress has stalled. It means progress has changed its character. When you live inside a universe that still keeps secrets, knowledge becomes something other than conquest. It becomes navigation. You learn where the ground is solid and where it thins. You learn which questions lead to reliable answers and which ones lead to deeper questions instead. This kind of knowledge is quieter. It does not declare victory. It does not rush to closure. It moves carefully, aware that the map is always provisional. There is something deeply human about this shift, even though it unfolds at cosmic scales. In everyday life, certainty tends to shrink as understanding grows. Children want clear rules. Adults learn that context matters. Wisdom often involves knowing where answers stop being sharp. Cosmology, at its current stage, reflects that same maturity. The universe's secrets are not hidden behind a locked door we have yet to open. Many of them lie in regions where our usual concepts stop working smoothly. Time, cause, beginning, and even existence itself become less cooperative the closer we push toward extremes. That resistance is not hostility. It is structure. A universe that allows observers like us to exist is already performing an extraordinary balancing act. It operates across scales that dwarf intuition. It contains processes that unfold over billions of years and others that flash by in fractions of a second. It permits patterns stable enough to support life, yet dynamic enough to keep changing. Expecting such a system to reveal all of its foundations cleanly may be asking too much of any single framework. Instead, what we see emerging is a layered understanding. At one layer, the universe expands from a hotter past. At another, space and time behave according to relativistic geometry. At another, quantum rules dominate. At still deeper layers, we suspect connections that remain mathematically incomplete. None of these layers cancel the others. They coexist. Living inside this structure means accepting that some explanations work locally rather than globally. The Big Bang works exceptionally well as a description of our universe's expansion history. It may not describe the full architecture of reality. Both of those statements can be true at the same time. This realization can change how science feels emotionally. Instead of being a ladder that climbs toward final truth, it becomes more like a shoreline that gradually extends. Each step forward reveals more coastline, not less ocean. For many people, this is surprisingly calming. There is no pressure to arrive at the final answer. There is no obligation to resolve the deepest mysteries before resting. The universe is not waiting for us to finish understanding it in order to function. We are allowed to be partial observers. This matters especially when thinking about our own place in the cosmos. For a long time, humans struggled with the idea that we are not central. Earth is not the center of the solar system. The sun is not the center of the galaxy. The galaxy is not the center of the universe. Letting go of centrality was difficult, but it did not erase meaning. It relocated it. Letting go of a definitive cosmic beginning follows a similar pattern. Meaning does not vanish when origins become uncertain. It relocates from the start of the universe to the processes unfolding within it. Meaning becomes something that arises rather than something that was assigned. This has practical consequences for how we think about knowledge itself. If the universe keeps secrets, then humility becomes a strength rather than a weakness. Curiosity becomes more valuable than certainty. Patience becomes part of understanding. These qualities are not often celebrated in dramatic science narratives, but they are central to real scientific practice. They also align well with the experience of listening quietly, letting ideas pass without needing to resolve them immediately. You do not need to remember every detail. You do not need to decide which model is correct. You're allowed to simply notice how the question feels. Does the universe feel more open when its beginning is less rigid? Does it feel less threatening when uncertainty is acknowledged rather than denied? Many people find that it does. There is also a subtle shift in how we relate to time. If the beginning is not absolute, then the present is not merely an echo. It is an active region of cosmic history, one that matters in its own right. The moment you're in now is not simply far removed from the start. It is embedded in an ongoing structure that continues to generate complexity, awareness, and reflection. From that perspective, living inside a universe that keeps secrets is not a limitation. It is an invitation to participate without needing to dominate, to observe without needing to conclude, to understand without needing to finish. Science, at its best, models this attitude. It advances by refining questions, not just by collecting answers. It learns to live with provisional explanations while continuing to test them. Cosmology today sits comfortably in that mode. It knows where it is strong. It knows where it is uncertain. It does not confuse the two. The Big Bang, seen through this lens, is neither a myth nor a final truth. It is a reliable guide within a known region of cosmic history. Beyond that region, other guides may be needed. Those guides may look very different from what we expect. They may involve new mathematics, new concepts of time, or entirely new ways of thinking about existence. Or they may simply reveal that some questions dissolve when examined from the right angle. Whatever the case, the universe shows no sign of running out of depth, and that depth does not demand urgency. You do not need to solve the universe before sleeping. You do not need to hold the full weight of cosmic history in your thoughts. The universe has carried itself for billions of years without our intervention. Your role, in this moment, can be simpler. You are a part of the universe reflecting on itself, briefly, gently, without obligation to resolve what remains unresolved. The expansion continues. The background radiation drifts through space. Galaxies form and dissolve. Theories evolve. Questions remain open. Nothing about that requires tension. If anything, it allows for rest. And so, as this exploration slows, there is no final conclusion to reach, no definitive statement to end on. The universe does not end its story cleanly, and neither does our understanding of it. It continues, quietly, keeping some of its deeper structures just beyond our current reach. And we continue inside it, learning what we can, letting go when needed, and allowing the unanswered questions to exist without pressure, just as the universe itself does, moment by moment, without asking to be finished.